The Big Bang isn't the universe's first moment, it's the first moment we can see, a wall of heat where time itself goes silent. Push past it, and the rules that build reality, space, direction, cause and effect, start to dissolve. So what was the universe really like before the first light, and can before exist when time hasn't been born yet? Somewhere beyond our oldest light, the universe keeps its first pages sealed, yet the ink still bleeds through. We can read those stains in the sky if we learn a stranger kind of history. This film follows that trail. Subtle patterns in ancient radiation, the chemistry of the first minutes, and the geometry written into expansion itself. We will treat the cosmos like a crime scene, because origins do not announce themselves, they leave residues, and when we track those residues backward, the familiar props of reality begin to fail. Space becomes less like a stage and more like a relationship. What then could the universe have looked like when looking requires an observer, and an observer requires time? In the deepest sense, the question is not only what existed, but what it could mean to exist, before clocks, before directions, before any stable rule could be trusted to hold. The word before sounds simple, until you ask what it is made of. So we will build a disciplined timeline from the last places evidence remains unbroken. We start with the moment the universe first became transparent, when light finally travelled freely and the sky took its earliest photograph. We step earlier, into the era when nuclei formed, when the universe chose how much helium to keep and how many fragile traces to leave behind. Then we press onward toward the frontier where our equations stop behaving like laws and start behaving like warnings. At that boundary, the story becomes an argument between possibilities. Perhaps the beginning was not a beginning at all. Perhaps the universe rebounded from a prior phase, carrying forward faint distortions like bruises under skin. Perhaps our cosmos is only one region in a far larger process, where beginnings occur repeatedly and locally, while the larger background never truly ends. Or perhaps the most unsettling option is the most precise, that time is not fundamental, and the earliest state is not a moment but a rule for how moments emerge. Each proposal must face the same tribunal, and it is not philosophy. It is the sky's black body curve, the fine-grained speckle of temperature variations, the acoustic ringing that shaped galaxies, and the elemental abundances that refuse to lie. We will see how a universe that is opaque can still be measured, how a history we cannot witness can still be constrained, and how imagination is allowed only when it pays its debts to data. Along the way, we will meet the singularity, less a point in space than a sign that our description has reached its limit. We will ask what quantum theory demands when gravity becomes strong, and what gravity forbids when quantum measurements become too sharp. We will navigate ideas that sound like metaphors, hidden dimensions, holographic boundaries, vacuum states that decay until they become concrete enough to test. And we will return, again and again, to one stubborn requirement. Whatever preceded our hot beginning must still produce the universe we actually observe. Not a universe that feels intuitive, not a universe that matches a preferred story, but this one, its structure, its smoothness, its small imperfections, and its arrow of time. If there is a prehistory, it must leave fingerprints. If there is no meaningful prehistory, that too must show up as a limit that evidence cannot cross. By the end, before the Big Bang will look less like a hidden room behind a door and more like a stress test for reality's foundations. The reward is not a neat picture you can hang on a wall, but a sharper sense of what questions nature permits and what kinds of answers the universe is willing to sign. We begin with what remains, and we follow it until the idea of a beginning either breaks or transforms. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will move from the meaning of time itself to the sky's earliest fossils, and then to competing origin stories that risk being testable. And at each step we will ask what the universe can reveal, without granting it a single unearned assumption. Begin with subtraction. Remove galaxies, spiral arms, dust lanes, and the pale bridges between clusters, until the map of the cosmos thins into scattered points. Remove stars, and the night loses its glittering anchors, leaving only a faint uniform glow that seems to come from everywhere at once. Remove planets, and there is no longer any sense of up or down, only a drifting geometry without landmarks. Now remove the thin background light itself. Keep subtracting past atoms, past nuclei, past particles, past the fields that let particles exist as excitations. Keep going until even space feels like a question, not a container, and distance becomes an idea with no ruler attached. We arrive at a word we use carelessly: nothing. Is it a physical state with properties, or a linguistic trap that hides ignorance behind a neat syllable? This documentary starts at that edge, where intuition fails and grammar misleads, and where the mind still tries to picture a stage. We ask what the universe really looked like before the Big Bang, and we immediately collide with the limits of the question. In modern cosmology, the Big Bang is not an explosion inside space, with debris flying outward into a waiting void. It is the rapid expansion of space and time together from a hotter, denser earlier state, described by a changing scale factor rather than a blast front. If time is part of what began, what could earlier even mean, and what would it be measured against? The word before assumes a timeline that already exists, as if there were a cosmic hallway with a clock on the wall. It assumes a clock that keeps ticking in some external arena, independent of what happens inside the universe. But general relativity ties time to the geometry of space-time, and geometry responds to energy and momentum. Clocks are physical processes inside the universe, not spectators outside it, and they are affected by motion and gravity. A second is not a universal substance. It is a comparison between processes, whether atomic vibrations or the swing of a pendulum. When we push our equations toward the beginning, we are also pushing the meaning of time toward its limits, because the very conditions that define clocks become extreme. So we set a rule. We will not treat the Big Bang as a fireball thrown into emptiness, because that picture smuggles in an outside space. We will treat it as a boundary in our description, defined by what our best models can track without contradiction. We will separate what we can observe from what we can only imagine, and we will be honest about what the evidence can and cannot say. First, clarify the stage. The observable universe is not the entire universe. It is the region whose light has had time to reach us since the early hot phase. That horizon is not a wall in space, but a limit in information, defined by the finite speed of light and the finite age of the cosmos. Beyond that horizon may be more space, more matter, or different conditions we cannot access directly, no matter how powerful our telescopes become. When people picture the Big Bang as a point, they often picture the observable universe shrinking into a dot, like a balloon collapsing to a pin. In the standard model, every region expands, and there may be no center at all, because expansion is not motion through space. It is the stretching of the metric, the rulebook, that tells us how to measure distances, so that galaxies can recede without traveling through a central location. Expansion is measured, not assumed. In the 1920s, Edwin Hubble and others compared galaxy distances to their spectral shifts, and a pattern emerged that still shapes our language today. Distant galaxies show redshift, and the pattern matches a universe that has been stretching for billions of years, with recession speed proportional to distance. The light is not simply Doppler shifted by motion, it is also stretched by expanding space, lengthening wavelengths as the universe grows. The cosmic microwave background, discovered in 1965 by Arno Penzias and Robert Wilson, shows a nearly uniform afterglow that fills the sky. It is cooled by expansion from an early furnace to a faint microwave whisper, now only a few degrees above absolute zero. Its tiny variations, temperature differences of tens of microkelvin, seeded structure, marking where matter was slightly denser, and gravity could later amplify the contrast. The abundances of light elements match a brief early period of nuclear reactions in a hot plasma, when the universe was minutes old. Hydrogen remains dominant, helium forms at about a quarter by mass, and traces of deuterium and lithium appear in amounts that depend sensitively on density and expansion rate. These clues do not show an explosion into space. They show space itself changing scale, carrying matter and radiation along with it. Now the limit. If we run general relativity backward, density rises and curvature grows, and the smooth universe we see today becomes hotter and more compact. In simple models, the math points to a singularity, a moment where quantities blow up to infinity and the equations stop giving finite answers. That sounds like a physical point of infinite density, but in physics, infinities usually mean a theory is being used beyond its domain. The singularity is likely a sign that general relativity is incomplete at extreme energies, where quantum effects cannot be ignored. General relativity treats space-time as a smooth fabric, while quantum theory insists that nature has fluctuations and uncertainty at small scales. When densities approach the Planck scale, the energy in a tiny region becomes so large that the geometry itself should fluctuate, and the classical picture may dissolve. This matters because the word before depends on what replaces that breakdown. If quantum effects of gravity become dominant, the earlier state may not be a singular point, and the boundary could soften into something more subtle. It could be a bounce, a transition, or a region where classical time is not well defined, as if the coordinate we call time becomes unreliable. Or it could be that our concept of time emerges only after some threshold, like temperature emerging from many particles, meaningful only when there are enough degrees of freedom to average over. The question becomes less about earlier events, and more about how time itself becomes a usable coordinate, one that can order change without contradiction. In everyday life, time feels like a river, but in physics, it is a parameter tied to measurement and to the structure of laws. If space-time is dynamic, then time is not a backdrop. It is part of the system whose origin we're trying to describe. That is why the grammar of before can become a trap, even when the curiosity behind it is legitimate. To keep our footing, we use time markers, each one a boundary between what is tested and what is inferred, and each one linked to a physical change. At about 380,000 years after the hot beginning, the universe cools enough for electrons to bind to nuclei, forming neutral atoms. Photons stop scattering constantly off free charges and begin to travel freely, turning an opaque fog into a transparent cosmos. That moment is recombination, and its light is the cosmic microwave background, a spherical shell around us in every direction. Visually, it is as if the universe finally opened its shutters, letting radiation stream outward after ages of confinement. It is our oldest direct image, not of the first moment, but of the first transparent universe, a snapshot of conditions when matter and radiation decoupled. Earlier than that, the universe is opaque plasma, a seething mixture of electrons, nuclei, and photons in near-constant interaction. We cannot see through it with light, because photons scatter too often to carry a straight-line message, but we can still infer its conditions, because the physics of that plasma leaves measurable consequences later. The spectrum and polarization of the microwave background, for example, still carry imprints of acoustic waves that rippled through the early fluid. In the first few minutes, nuclear synthesis builds light nuclei, and the universe briefly functions like a nuclear reactor without walls. As temperatures fall below a critical point, protons and neutrons can bind without being immediately blasted apart by high-energy photons. The ratio of neutrons to protons, set by weak interactions and cooling, largely determines how much helium forms, while deuterium abundance acts like a sensitive gauge of density. Those ratios are measured in ancient gas clouds and old stars, and they match a hot, dense early phase with remarkable precision. This is one of the strongest pillars under the Big Bang model, because it connects microphysics to cosmic history in a way that can be checked. It also shows how the early universe is not merely guessed. It is constrained by numbers, by observed fractions that would be different if the early expansion were faster or slower. Go earlier, and the clock becomes less familiar, because the energies are far beyond ordinary matter. Around a trillionth of a second, the electroweak era, the electromagnetic and weak forces are not yet distinct in the same way we experience them now. Particle interactions are governed by symmetries that later break as the universe cools, like a perfectly balanced system choosing a direction when conditions change. We cannot recreate the whole universe, but we can test parts of this physics in accelerators, where high-energy collisions briefly mimic early conditions. The discovery of the W and Z bosons and later the Higgs field's role in symmetry breaking gives substance to this timeline. That gives us partial confidence in the narrative, even when we cannot observe it directly, because the same equations that describe collider events also shape our early universe models. Then we reach the Planck time, about 10 to the minus 43 seconds, a number so small it resists intuition. This is not a measured moment. It is a signpost built from constants, C, G, and H, where quantum gravity should matter. Beyond it, our current equations stop being reliable, not because reality ends, but because our descriptions lose their footing. We do not know whether space-time is smooth, discrete, fluctuating, or something more abstract, like a network of relations rather than a continuous fabric. We do not know whether time flows, branches, or emerges from deeper relations, because we do not yet have a tested theory that unifies gravity with quantum mechanics. The Planck time is the edge of tested physics, not the start of reality, and it marks a horizon in understanding rather than a literal beginning. At this edge, the central question splits into two, and both are unavoidable. One is physical: what state preceded the hot, dense phase that our evidence supports, and what dynamics led into it. The other is conceptual: is there a meaningful sense in which proceeding is defined when time itself is part of the system? Some proposals keep the word before but change the mechanism, while others dissolve the word before and replace it with a different kind of ordering. Even the phrase initial conditions becomes slippery here, because initial usually means chosen at a time, and time is exactly what is under dispute. If time emerges, then the earliest description might be more like a boundary condition in a mathematical structure than a moment on a clock. That idea can feel abstract, yet it is grounded in a practical demand. Our theories must remain self-consistent when pushed to extremes. To investigate, we need a method that does not collapse into speculation, and we need language that does not pretend to know more than it does. This documentary follows three pillars. First, what observations tell us, including the expansion history, the microwave background, element abundances, and large-scale structure. Second, what theories require, including general relativity, quantum field theory, and the consistency conditions they impose on energy, causality, and symmetry. Third, what might be testable in principle, even if it is difficult in practice. That includes signatures in the microwave background, relic particles that might survive from the early epochs, and gravitational waves that could carry information from earlier times. The key is restraint. We privilege ideas that could, at least in principle, leave an imprint that distinguishes them from rivals. Otherwise, the phrase, "before the Big Bang," becomes a canvas where any story can be painted without risk. Think of the early universe as a crime scene. We arrive long after the event, and the scene has been altered by cosmic evolution, like footprints softened by wind and rain. Expansion stretches and dilutes traces, turning sharp features into broad patterns. High energies erase delicate correlations because thermal equilibrium smooths differences and drives systems toward uniformity. Later processes can mimic earlier signals, and noise can masquerade as discovery, especially when the sought-after imprint is subtle. Still, the universe carries evidence, and the evidence is not arbitrary, because different histories leave different statistical fingerprints. The microwave background is a photograph of a later surface, but its tiny fluctuations encode earlier physics, including the spectrum of primordial perturbations and the geometry of space. Element abundances are a chemical record of minutes-old conditions, and they are surprisingly unforgiving of careless models. The expansion rate is a dynamical record written into distances and redshifts, and it can be cross-checked with supernovae, baryon acoustic oscillations, and other cosmic rulers. In this sense, cosmology is not only storytelling, it is forensic accounting, balancing equations against data with little room for improvisation. There may be other clues. A background of primordial gravitational waves could pass through the plasma without scattering, because gravity couples weakly and does not get trapped the way light does. In principle, it could carry information from extremely early times, even from near the Planck regime, as ripples in spacetime itself. But in practice, such signals are weak and hard to separate from astrophysical sources, and even our best detectors strain to hear them. Some fingerprints may be forever smudged, not by conspiracy, but by the laws of thermodynamics and the violence of the early state. When the universe is hot enough, particles are created and destroyed in abundance, and memory of specific arrangements is lost in the churn. That does not mean the past is unknowable. It means the past is compressed into a few robust patterns that survive the heat. The question becomes, which patterns are robust enough to reach us, and which are erased by nature's own mixing? This is why the phrase "before the Big Bang" is both irresistible and dangerous. It invites a picture of a dark emptiness waiting to be lit, a stage with curtains drawn. It suggests a moment when something exploded into nothing, as if nothing were a container with volume, but the evidence points to a different story. The Big Bang is a description of a hot beginning and an expanding spacetime, not a detonation at a location. The beginning in our equations is a boundary where our tools break, not a filmed event stored on some cosmic archive. When we ask for a first frame, we may be asking for something the universe does not provide, at least not in the way our minds expect. Yet the desire to ask is not a mistake. It is a signal that our everyday concepts are being stretched to match a reality that is larger than experience. So we refine the question. Instead of asking what happened before, we ask what the earliest reconstructible universe was like, and what kinds of earlier scenarios could leave traces without contradicting what we already measure. We ask whether time had a first tick, or whether our tick marks fail near the origin, like a ruler that warps when brought too close to a fire. We ask whether nothing is a state with measurable structure, or whether it is a word that marks the edge of explanation. The stakes are not only philosophical, because early universe mechanisms shape what we see in the sky today. If the early universe included inflation, bounces, or phase transitions, those mechanisms shape the distribution of matter and the seeds of galaxies, influencing the pattern of clustering across billions of light years. If space-time is emergent, then the laws we treat as fundamental may be effective, like fluid equations that arise from molecules, accurate at large scales but incomplete at the smallest ones. If quantum gravity resolves the singularity, then the universe may have a prehistory, even if it is not ordered by ordinary time. That possibility changes how we interpret origin, because an origin might be a transition in description, rather than a creation from absolute nothing. It also sharpens a more personal question. When we say the universe began, are we naming a physical event, or are we naming the point where our current language stops working? We end this chapter with a practical pivot. The ambiguity of before does not stop the investigation. It tells us where to look and how to speak with discipline. We can move forward by moving closer to the beginning, step by step, using the oldest light, the oldest chemistry, and the oldest dynamics we can read. Next, we reconstruct what the universe looked like when it first became visible, and we follow the trail backward toward the edge of time. We cannot watch the beginning directly, because the early universe was not a clear stage with visible actors. We can only reconstruct the young universe from what survived, then ask what any earlier story must reproduce. That constraint, evidence first, imagination second, sets the tone for everything that follows. The oldest light we can see is not the first light ever made, and that distinction matters. It is the first light that could travel freely without being scattered back into the fog. When we say first light in cosmology, we usually mean the first light that stayed visible. For hundreds of thousands of years, the universe was a hot plasma, dense enough to behave like a glowing, electrically charged fluid. Electrons and nuclei stayed separate, because thermal energy kept them from binding into atoms. Photons could not stream in straight lines, because they scattered constantly off free charges. In visual terms, imagine a brilliant interior of a star stretched across all of space, bright, opaque, and restless. Light did exist, but it was trapped in a perpetual crowd, ricocheting from particle to particle. Every attempted beam became a random walk, and seeing across distance was physically impossible. As expansion cooled the plasma, a threshold arrived, and the chemistry of the cosmos abruptly changed. Electrons bound to nuclei and neutral atoms formed, and photon scattering dropped sharply. The universe did not suddenly create light, it finally stopped imprisoning it. That transition is recombination, about 380,000 years after the hot beginning, when temperatures fell to roughly a few thousand Kelvin. Protons and electrons combined mostly into neutral hydrogen, with helium already present from earlier nuclear reactions. With far fewer free electrons, the dominant scattering process weakened, and the fog thinned. The universe became transparent, and radiation decoupled from matter, meaning photons stopped sharing a common temperature through constant collisions. From that moment onward, the radiation mostly coasted, while matter began evolving under gravity with less pressure support. It is a clean break in behavior, one of the sharpest phase changes in cosmic history. The cosmic microwave background is that released radiation, stretched by expansion into microwaves as space itself grew. Today its mean temperature is about 2.725 Kelvin, only a few degrees above absolute zero, yet it remains astonishingly bright in photon number, filling every cubic centimetre with relic light. The CMB is a surface of last scattering, not a wall at the start of time, and the geometry is subtle. It is a time capsule that begins only when the fog clears, not when the universe begins. When we look at it, we are not looking at the birth, we are looking at the first clear photograph. We see it as a sphere around us because we look back along our past-like cone and time becomes distance. In every direction, we intercept photons last scattered far away from a shell whose radius is set by how long light has travelled. Another observer elsewhere would see a different sphere centred on them. No one has a privileged viewpoint. On screen, the CMB is often shown as a mottled oval map, a full sky projection like a peeled orange laid flat. The colours look dramatic, but the underlying variations are extremely small, and the palette is exaggerated for visibility. That artistic choice hides a deeper truth. The universe was almost perfectly uniform. The CMB is almost uniform, and that uniformity is itself a clue about the early state. It says the early universe was extremely smooth, hot, and close to thermal equilibrium, like a near-perfect blackbody radiator. In laboratories, blackbody spectra require careful isolation. The early cosmos produced one naturally, yet it is not perfectly uniform, and the imperfections matter because they are the beginnings of structure. Temperature anisotropies are at the level of about 1 part in 100,000, a faint grain in an otherwise even glow. Those tiny differences are the fingerprints of primordial physics. These variations are the seeds of everything later, including every galaxy, star and planet that would eventually form. They mark slightly denser regions that gravity could amplify into galaxies and clusters, while underdense regions became voids. The cosmos is a magnified version of its own early noise. The anisotropies are not random noise in the everyday sense because their pattern has a specific statistical structure. Their statistics and angular pattern carry a record of the early plasma's sound waves, frozen into the sky. The CMB is not only a picture, it is a spectrum of vibrations. Before recombination, photons and baryons behaved like a coupled fluid, tied together by frequent Thomson scattering. Gravity tried to compress overdense regions, and radiation pressure pushed back, because photons resist compression. The result resembles a drumhead being struck, oscillations launched into the primordial medium. This tug-of-war launched acoustic oscillations, and different wavelengths behaved differently as the universe expanded. Some modes had time to complete multiple compressions and rarefactions, while others barely began their first cycle. Different modes were caught at different phases when the universe turned transparent. That freezing in produces acoustic peaks in the CMB power spectrum, a plot that compresses the sky into a set of characteristic scales. The peak positions and heights encode geometry and cosmic ingredients, like a chemical assay performed with light. A small change in content shifts the entire pattern. The first peak corresponds roughly to the sound horizon at recombination, the maximum distance a sound wave could have travelled in the coupled plasma. That scale becomes a standard ruler, set by microphysics and the expansion rate. In the power spectrum, it appears as a preferred angular size on the sky. Baryons add inertia to the oscillating fluid, making it harder for pressure to push matter back out of gravitational wells. They enhance compressions relative to rarefactions, shifting the odd and even peak heights in a distinctive alternation. This is why the CMB can weigh ordinary matter. Dark matter behaves differently because it does not couple to photons, so it does not feel radiation pressure in the same way. It deepens gravitational wells early, shaping peak locations and the growth of structure long before atoms formed. In effect, it provides the scaffolding on which baryons later settle. Radiation affects the expansion rate and the early gravitational potentials, especially when the universe was young and energy densities were high. It leaves subtle signatures in damping and in the early integrated sacs, Wolf effect, where evolving potentials slightly shift photon energies. These are small corrections, but precision cosmology lives on small corrections. Neutrinos act like radiation when they are relativistic, and in the early universe they carried a significant fraction of the energy budget. Their free streaming changes the phase and amplitude of acoustic features in measurable ways, because they do not cluster efficiently on small scales. Even without catching a neutrino directly, we can sense its gravitational influence. The small-scale CMB is also blurred by diffusion, because photons still scatter enough to smear out tiny features. Photon random walks erase fine structure, producing silk damping at high multipoles, where the map looks smoother than it otherwise would. The universe itself applies a soft focus filter to its earliest photograph. From these patterns we infer a specific cosmic recipe, and the remarkable fact is how few ingredients are needed. A universe with ordinary matter, cold, dark matter, and a cosmological constant fits with striking consistency across many datasets. The fit is not casual. It is quantitative, down to the percent level. This baseline is called LCDM, where L denotes dark energy in its simplest form and CDM denotes cold dark matter. It is not a claim of final truth, but it is the most successful compact description of the data we have. In science, the best model is the one that survives the most independent attacks. LCDM uses a small set of parameters to match many observables, which is part of its power and part of its vulnerability. It links the CMB, galaxy clustering, lensing, and the expansion history into one coherent narrative. When the same numbers explain multiple phenomena, coincidence becomes unlikely. The model's success creates a standard that alternatives must meet, not only qualitatively but in precise statistical detail. Any pre-Big Bang scenario must flow into something that looks like LCDM by recombination, or it will fail the sky's own audit. The CMB does not negotiate with speculation, so we set a rule. We treat the CMB not as mythology, but as a calibration target for any earlier epoch. Whatever happened before transparency must deliver the correct spectrum, the correct anisotropies, and the correct acoustic pattern. The CMB also carries polarization, which adds another layer of evidence beyond temperature alone. Thomson scattering of an anisotropic radiation field produces linear polarization, because scattered light prefers certain directions. Polarization is faint, but it is information-rich. E-mode polarization traces the same acoustic physics with different systematics, and it appears in a swirling gradient-like pattern on the sky. It tightens constraints on parameters and checks the temperature story, because the peaks line up in a predictable phase relationship. When two independent channels agree, the reconstruction becomes harder to dismiss. B-mode polarization is different and more elusive because it has a Kerr-like pattern that ordinary density fluctuations do not easily produce. It can be generated by gravitational lensing, as intervening matter subtly twists E-modes into B-modes. In that sense, B-modes are also a map of the universe's later structure. If inflation produced a background of tensor modes, it could imprint a distinctive large-angle B-mode pattern, strongest on broad swaths of the sky. Searches continue, and limits are already strong, forcing many simple inflationary models into narrower corners. The silence is not empty, it is informative. The absence of a detected primordial B-mode is not a failure of cosmology, because null results still carve away possibilities. It narrows the space of early universe dynamics and energy scales, telling us how violent the earliest expansion could have been. Sometimes the universe speaks by refusing to shout. The CMB is one pillar, but it is not alone, and cosmology rarely trusts a single witness. The universe also left a map in the distribution of matter across enormous distances, a fossil record written in galaxies. Where the CMB shows the embryo, large-scale structure shows the adult. Large-scale structure is the grown-up version of the CMB anisotropies, shaped by gravity over billions of years. The same initial perturbations evolved under gravity into filaments, clusters, and voids, forming a cosmic web that spans hundreds of millions of light-years. In simulations, it looks like neural tissue. In the sky, it becomes a statistical pattern. Galaxy surveys measure this structure statistically, because no single cluster tells the whole story. They infer a matter power spectrum and compare it to predictions from early initial conditions, accounting for bias and selection effects. The match is not perfect in every detail, but the broad agreement is striking. Baryon acoustic oscillations appear again in this map, like a faint echo of the primordial sound waves. The same sound horizon becomes a preferred scale in galaxy clustering, visible as a small bump in the correlation function. It is a delicate imprint, but it persists across cosmic time. BAO acts as a standard ruler, because its physical length is set early, and then carried forward by expansion. Its measured size at different redshifts tracks how the expansions stretch distances over time. In effect, we lay a ruler across the universe and watch it grow. To connect these rulers and maps, we need the expansion history, which is the backbone of the entire reconstruction. Redshift is our primary observable, and it encodes how wavelengths stretch with the scale factor. A spectrum becomes a time machine when its lines slide predictably. In an expanding universe, light is redshifted because space itself expands, stretching wavelengths as they travel. It is metric expansion, not galaxies flying through space from a central blast, and the difference is conceptual but crucial. The universe is not an explosion into emptiness. It is the growth of the distant scale itself. There is no privileged center in the standard picture, because the expansion happens everywhere in the same way on large scales. Every observer sees distant galaxies receding in a pattern consistent with homogeneity, and the same Hubble law emerges from any location. The center is not a place, it is a misunderstanding. The Hubble parameter describes the rate of expansion at a given time, and it changes as the cosmic energy budget changes. Its present value is measured locally and inferred globally, and the comparison is informative because it tests consistency. When different methods disagree, we learn either about systematics or about missing physics. Type Ia supernovae provide standardizable candles because their light curves correlate with intrinsic luminosity. Their brightness versus redshift reveal that expansion is accelerating, consistent with dark energy or L. On screen, the supernova data appear as a gentle curve that refuses to match a decelerating universe. BO provides geometric distances that cross-check supernovae, and it does so with very different sources of uncertainty. Together, they constrain the late-time expansion and the matter density, tightening the allowed histories. The universe becomes a solved puzzle only when multiple pieces interlock. Galaxy clustering and weak lensing add growth information, which is complementary to pure geometry. They test how structures form under gravity, not only how distances scale, by measuring how matter clumps and how it bends light. Lensing maps, in particular, turn invisible mass into visible distortion. The CMB anchors the early time conditions, providing a starting line with well-measured initial fluctuations. It predicts a late-time universe, and surveys test whether that prediction holds as structures grow and expansion accelerates. This is why cosmology can be both historical and predictive. This is how cosmology becomes a closed evidentiary loop, with early physics feeding forward into late observables. Early conditions set initial perturbations, and late observations test the consequences across billions of years. If the loop closes tightly, the reconstruction earns trust, yet one more pillar reaches even earlier than recombination, into a time when the universe was not hundreds of thousands of years old but minutes old. The light elements were forged when the cosmos was hot enough for nuclear reactions, yet cool enough for nuclei to survive. In that brief window, the universe performed its first chemistry. Primordial nucleosynthesis happened when temperatures fell enough for nuclei to survive photodisintegration, roughly within the first several minutes. Protons and neutrons combined into deuterium, helium, and small traces of lithium, following a network of reactions with well-studied cross-sections. The result is a set of abundances that can be measured today. The key control knob was the baryon-to-photon ratio, which sets density during nucleosynthesis and therefore reaction efficiency. Another control knob was the expansion rate, which sets reaction time by determining how quickly the universe cooled. If expansion is too fast, reactions freeze out early. If too slow, they run longer. Helium-4 abundance depends strongly on the neutron-to-proton ratio at freeze-out, because almost every available neutron ends up bound in helium. That ratio depends on weak interaction rates and the cooling history, which together determine when neutrons stop converting into protons. Neutron decay then quietly reduces the supply before nuclei assemble. Deuterium is especially sensitive to density, which is why it is often called a baryometer. Higher baryon density burns deuterium more efficiently, leaving less behind, while lower density preserves more deuterium. A small change in density produces a noticeable change in the final deuterium fraction. These abundances are measured in metal-poor environments and compared to nuclear reaction networks, because later stellar processing can alter the pristine ratios. The match supports a hot early phase and constrains parameters that also appear in the CMB. Two very different epochs, minutes and hundreds of thousands of years, agree on the same baryon density. BBN also constrains the number of light species, because extra relativistic energy density speeds expansion during nucleosynthesis. Faster expansion changes predicted helium and deuterium yields, and the data allow only limited room for additional components. This is one reason cosmology can test particle physics beyond accelerators. That constraint links cosmology to particle physics, turning the early universe into a laboratory for hidden sectors. It limits dark radiation and motivates careful accounting of neutrinos, including their temperature and decoupling details. The cosmos is not just a backdrop for particles, It is a detector. So far, the story is coherent from minutes to hundreds of thousands of years, and that coherence is itself a remarkable achievement. We can move from nuclear reaction networks to plasma acoustics and find a consistent set of parameters. But the central question presses earlier, toward the hidden interval that no photon can show us. Between the Planck scale and recombination, the universe is readable only indirectly, and that indirectness shapes the way we talk. We infer it by consistency across multiple independent relics, each sensitive to different physics. The reconstruction is like triangulation from distant lighthouses, not a direct walk through the past. One major inference is the origin of the initial perturbations because the CMB does not merely show fluctuations, it characterizes them. The CMB shows they were adiabatic, nearly Gaussian, and close to scale invariant, which is a highly specific combination. It is hard to get that trio by accident. Adiabatic means different components fluctuated together, so a denser region had proportionally more photons, baryons, and dark matter. Nearly Gaussian means the fluctuations resemble a random field with a simple statistical distribution, with only small deviations allowed. These properties are clues about a mechanism that acted before recombination. Scale invariance means fluctuations have similar power across logarithmic scales, so no single length scale dominates the pattern. Observations show a slight tilt, with NES a bit less than 1, indicating slightly less power on small scales than perfect scale invariance would predict. That tiny tilt is measured with impressive precision. That tilt is a fingerprint of a mechanism, not a decorative detail added to make plots interesting. It constrains how the early universe generated and stretched perturbations, and it disfavors many naive scenarios. In cosmology, small numbers often carry the most weight. Inflation is the standard mechanism proposed to explain these features, and its appeal is partly that it solves several problems at once. It posits a period of accelerated expansion in the very early universe, driven by a high-energy field with negative pressure. In simple terms, space expanded so rapidly that causal patches were blown up to cosmic size. Inflation addresses the horizon problem, which begins as a question about thermal contact. Regions far apart on the CMB sky look thermally correlated, even though simple expansion gives them no time to equilibrate. Inflation makes them neighbours in the pre-inflationary patch, then stretches that patch across the observable universe. Inflation addresses the flatness problem, which is a statement about instability in the standard expansion. The observed spatial curvature is close to zero, and inflation drives curvature toward near flatness by rapidly increasing the scale factor. It is like smoothing a crumpled sheet by pulling it taut. Inflation addresses the monopole problem, which arises in many grand unified theories that predict heavy relics. Those relics would overclose the universe if produced abundantly, yet we do not see them. Inflation dilutes them to negligible abundance by expanding space faster than they can remain significant. Inflation also provides a perturbation generator, which is where the story becomes most conceptually daring. Quantum fluctuations of fields are stretched to cosmic scales and become classical density perturbations, because expansion freezes their phases and locks in their amplitudes. What begins as vacuum noise becomes the blueprint for galaxies. This is a profound claim with a testable output, and cosmology has spent decades checking its consequences. It predicts a nearly scale-invariant spectrum and specific relationships among temperature, polarization, and non-Gaussianity. It also predicts correlations between E-modes and temperature that have been observed. Historically, the inflationary idea gained traction in the early 1980s, when theorists sought a mechanism to resolve the horizon and flatness puzzles. Later, satellite missions like COBE, DBMAP, and Planck transformed inflation from an elegant proposal into a framework confronted by precision data. Each mission sharpened the questions, and each narrowed the plausible space of models. But inflation is not proven as a unique history, and that caution is part of the honest narrative. Many inflation models exist, and some alternatives mimic its predictions while changing the prehistory. When multiple stories fit the same evidence, the evidence has not yet selected a single script. The data favours the broad inflationary template, but it does not yet identify the inflaton or the exact potential that would have driven accelerated expansion. The mechanism remains a successful patch, not a closed case, because we have not pinned down the underlying microphysics. In science, works is not the same as explained. If inflation happened, it may have erased much of what came before, and that possibility changes how we interpret the silence. Accelerated expansion can dilute prior structures and make earlier conditions observationally inaccessible, leaving only a reset set of initial conditions. Inflation, in that sense, is both a solution and a veil. That erasure is part of the narrative tension, because it suggests our best evidence may be evidence of a process that hides its own prelude. Our measurements are exquisite, yet they may be measuring the aftermath of an information-destroying expansion. What if the universe's earliest chapter was edited out by the universe itself? Still, some signals could reach earlier than light, because not everything interacts like photons do. They would need to decouple earlier, interact weakly, or be carried by spacetime itself. Cosmology therefore looks for messengers that slip through the plasma without being scattered into forgetfulness. A cosmic neutrino background should exist from when neutrinos decoupled about 1 second after the hot beginning, when weak interactions became too slow to keep them in equilibrium. It has not been detected directly, because relic neutrinos today are extremely low energy and elusive, yet its effects are inferred through precision measurements. Neutrinos leave imprints on the CMB and structure through their energy density and free streaming, subtly altering peak shapes and suppressing small-scale clustering. These indirect detections are consistent with a relic background, and they even constrain the sum of neutrino masses. It is a shadow measurement, but it is still a measurement. Primordial gravitational waves could carry information from extremely early times, because they are ripples of spacetime rather than particles moving through it. They would propagate with little scattering, preserving a memory of the expansion history across otherwise opaque epochs. If detected, they would be a direct probe of energy scales far beyond any terrestrial experiment. We search for them through CMB B modes and through direct detectors at higher frequencies, because different experiments are sensitive to different wavelengths. Each band probes different epochs and different sources, from inflationary scenarios to later astrophysical backgrounds. The challenge is separating a primordial whisper from a noisy universe. Topological defects are another possible relic, hinted at by theories in which symmetries break during early phase transitions. Cosmic strings or textures could form and leave distinctive signatures, such as line-like discontinuities in maps or characteristic gravitational wave backgrounds. Their appeal is that they would be unmistakably non-inflationary in flavour. Most defect scenarios are strongly constrained by CMB anisotropies, lensing and pulsar timing, because defects would add extra structure that we do not observe. The constraints are themselves informative about early symmetries, limiting how and when such transitions could have occurred. Even absence becomes a boundary condition on theory. All these relic channels share a theme, and it is easy to miss in the excitement of the data. They are not pictures of the beginning, but filters that pass only certain kinds of information, while discarding the rest. The early universe is not hidden because it is mystical. It is hidden because it is opaque. The universe is readable because it is lawful, not because it is transparent, and that is a subtle kind of comfort. We reconstruct by matching multiple datasets to a single, consistent history, and we demand that the same parameters work everywhere. The method is conservative, but the implications are radical. Yet the reconstruction has a hard boundary, and it appears when we push our equations beyond their tested domain. When we push backward, densities rise and our classical description strains, because energy scales climb toward regimes where quantum effects cannot be ignored. The mathematics begins to warn us that we are extrapolating. General relativity run in reverse points toward a singularity in simple models, where curvature and density blow up without bound. Infinities usually signal that a theory is being used beyond its domain, not that nature literally contains infinite quantities. A singularity is often a signpost that says, new physics required. Near the Planck scale, around 10⁻⁴ seconds, quantum gravity should matter, and our familiar categories may fail. Spacetime itself may fluctuate, and the notion of a smooth metric may break down into something discrete or emergent. At that scale, where and when may not behave like coordinates on a map. This is where the word before becomes unstable, because time is not merely a background parameter in general relativity. If time is part of the dynamical system, then earlier may not be a well-defined direction in the way we intuitively imagine. We are used to time as a line. Quantum gravity may treat it as something stranger. Some proposals keep time and replace the singularity with a bounce, where contraction precedes expansion, and the universe passes through a minimum size. Others replace the beginning with a transition where classical time emerges from deeper degrees of freedom, like temperature emerging from molecular motion. The details differ, but the demand is the same: recover the successful late story. Whatever the correct theory is, it must reproduce the evidentiary backbone we have built, because that backbone is not optional. It must yield the observed expansion history, element abundances, and CMB statistics, including the acoustic peaks and polarization correlations. A beautiful theory that misses the sky is still wrong. It must also explain why the universe is so uniform on large scales, without smuggling in fine-tuned initial conditions as an unspoken assumption. It must account for the origin of perturbations without violating causality or known physics, and it must do so quantitatively. The universe is not impressed by vague plausibility. This is the shadow cast by the first light, and it falls across every attempt to speak about origins. The CMB is a luminous boundary that reveals much, and it hides the most important moment, because it begins only after the fog clears. We can map the aftermath in exquisite detail, yet the trigger remains unseen. We have a detailed map of the universe after it became transparent, with temperature variations, polarization patterns, and a power spectrum like a barcode. We still do not know what set the initial conditions that map requires, or whether those conditions were inevitable. The data describe the starting line, but not the runner's first step. The central question remains sharpened, not softened, by the success of the reconstruction. Did anything exist before the Big Bang, and what could that have looked like if time was not yet classical? If before is meaningful, what physical clock could have been ticking? We end this chapter with a practical pivot. To talk about a before, we must confront the singularity and the need for quantum gravity. The next step is not to invent stories, but to ask what replaces the breakdown in our equations. Next, we follow the evidence to the edge of the equations, where precision meets uncertainty and the map ends. We ask what replaces the breakdown, and what signatures could survive from earlier epochs, slipping through the universe's long darkness into our instruments today. We have followed the evidence back to a hot, dense beginning, and the trail has narrowed into something like a mathematical corridor. Now we reach the place where our best equations stop answering, not because curiosity ends, but because the tools do. General relativity is a theory of geometry, and it is unusually literal about that claim. Matter and energy shape space-time, and space-time tells matter how to move through a precise relationship between curvature and stress energy. When we run those equations backward in time, the scale factor shrinks while curvature grows, and the familiar cosmic distances collapse into a tighter and tighter frame. In the simplest cosmological solutions, that backward evolution ends at a singularity, where the equations no longer give a sensible continuation. The Friedmann equations, which describe expansion in a homogeneous universe, drive density and curvature upward as the scale factor approaches zero. The mathematics does not merely become difficult, it becomes undefined in the way a map becomes useless at the edge of its paper. A singularity is not a point you can visit, and it is not a location with an address. In general relativity, it means geodesic incompleteness, where some world lines cannot be extended any further, even though the traveller's own clock would still have time left to tick. It also means curvature invariants diverge, so tidal forces become unbounded in the model, and any extended object would be stretched and squeezed without limit. Most importantly, it means the theory loses predictive power, because it stops producing finite, unique evolution from well-posed initial data. The equations are deterministic only where the geometry remains regular enough to define what next even means. At a singularity, the language of differential geometry breaks, and with it the promise that the future follows from the past. Popular language turns that into infinite density at a location, as if the universe began as a needle point of matter. That picture is a symptom of extrapolating a classical description too far, and it borrows intuition from ordinary objects that may not apply. The infinity is a warning label, not necessarily a physical object, and physics has learned to respect that kind of warning. In physics, infinities usually signal missing degrees of freedom or a breakdown of assumptions, not an actual measurable quantity. The ultraviolet catastrophe in 19th century radiation theory was an infinity, and it was cured by quantization. The self-energy of the electron in early field theory tried to become infinite, and it forced a deeper understanding of renormalization and effective descriptions. The assumption doing the most work here is smooth, space-time, continuous down to arbitrarily small scales. General relativity treats the metric as a differentiable field defined at every point, so it can speak in the language of derivatives and curvature tensors. Quantum theory says fields fluctuate, and measurements have irreducible uncertainty, so the very act of concentrating energy into tiny regions should stir the geometry. If you try to localize an event too sharply, you need high momentum, and high momentum means high energy. In ordinary quantum field theory, that energy can be treated as a source on a fixed background, but gravity makes the background respond. When energy is concentrated into tiny regions, the geometry itself should fluctuate, and the idea of a fixed grid of points becomes suspect. So we set a rule. When a theory predicts its own failure, we treat the failure as a boundary of applicability, rather than a literal description of reality. That boundary is not a defeat. It is a sign that we have reached the edge of one regime and need the next. That boundary is often described with Planck units, which are built by combining the constants that govern relativity, gravity, and quantum mechanics. The Planck length is about 1.6 times 10 to the minus 35 meters, a scale so small that even an atomic nucleus looks enormous by comparison. The Planck time is about 5.4 times 10 to the minus 44 seconds, a tick so brief that before and after start to sound like metaphors. The Planck energy is about 1.2 times 10 to the 19 GeV, far beyond any accelerator we can imagine building. It is not just technologically out of reach, it is conceptually distant from the energies that shape everyday matter. These numbers are built from C, G, and H, and they form a kind of dimensional handshake between the three pillars of modern physics. They mark where quantum effects of gravity cannot be ignored, because the gravitational field becomes sensitive to quantum uncertainty. They do not prove what happens there, but they tell us where classical intuition becomes unreliable, and where a smooth metric is likely the wrong starting point. Near that scale, the energy needed to probe smaller distances would strongly curve spacetime, and the probe would begin to disturb what it is trying to measure. A useful way to picture this is to imagine a microscope that works by throwing higher and higher energy at a target. In non-gravitational physics, higher energy means finer resolution, so the microscope gets better as you turn the dial. With gravity included, turning the dial eventually makes the target collapse behind its own horizon, and the microscope stops seeing more detail. It is tempting to say the universe began at the Planck time, as if that number names the first frame of a cosmic film. That is not what the signpost means, and the distinction matters for how we talk about origins. It means our current map ends there, and past that edge we need a quantum theory of spacetime itself. The history of this realization is part of the story, because it did not arrive all at once. Einstein's equations were published in 1915, and within a few years cosmological solutions were already being explored, sometimes reluctantly. By the late 1920s, expansion was becoming observationally real, and by the mid-20th century the hot Big Bang picture had gained traction. The Singularity theorems of the 1960s, developed by Penrose and Hawking, sharpened the issue with mathematical force. They showed that under broad conditions, energy conditions and causal structure, spacetime geodesics cannot be extended indefinitely into the past. The theorems did not say what the singularity is, but they said the classical theory cannot avoid something like it. That cannot avoid is precisely what makes the boundary so compelling, because it is not an artifact of a special model. It is a structural feature of classical gravity under reasonable assumptions, and it tells us where new physics must enter. The question becomes not whether general relativity is elegant, but whether it is complete. We already have a partial tool called quantum field theory in curved spacetime, and it is one of the most successful compromises in theoretical physics. It treats matter fields as quantum, while spacetime remains classical and fixed, like a stage that can bend but not fluctuate. That framework predicts particle creation in expanding universes, and it explains effects like Hawking radiation in principle, even when no particles were put in by hand. In an expanding universe, modes of a quantum field are stretched, and what looked like vacuum fluctuations can become real excitations. The mathematics is similar to a parametric amplifier, where changing the background pumps energy into the field. This is not just an abstract statement. It is the mechanism behind how tiny early fluctuations can later become the seeds of galaxies. It also reveals deep ambiguities that become fatal near the beginning, where the background changes rapidly and the notion of slowly varying fails. One ambiguity is the vacuum, because in curved or time-dependent spacetime there is no unique notion of a lowest energy state. Different observers can disagree on what counts as a particle, and their disagreement is not a matter of taste. In an expanding universe, the very definition of particle depends on how you slice time, which is a geometric choice rather than an experimental knob. If you choose one set of modes, you see a vacuum, and if you choose another, you see a bath of particles. The physics is consistent, but the language of what exists becomes frame-dependent in a way that feels unsettling near an origin. Another issue is back reaction, which is the polite word for a dangerous feedback loop. Particle creation changes the stress-energy tensor, and in general relativity that stress energy should change the geometry, which then changes the particle creation. In the semi-classical approach, we feed an expectation value into Einstein's equations, but near Planck energy's fluctuations are large, and the average may not capture what matters. Even defining that expectation value requires careful regularization, because quantum fields in curved space produce divergences that must be renormalized. The procedure works in many settings, but it depends on having a well-defined background and a clear separation of scales. Near the beginning, the separation collapses and the bookkeeping starts to look like wishful thinking. Most crucially, the semi-classical method assumes a background manifold with well-defined points, so fields can be evaluated here and there. Yet the question we are asking is whether points and intervals are meaningful at all at the smallest scales. If spacetime is quantum, geometry cannot be a passive stage, and the beginning problem is not only about matter in spacetime, it is about spacetime as an object that must be quantized or replaced, and that is a conceptual leap with consequences. Quantizing geometry means that distance, duration, and even causal order may become operators with uncertainty, not fixed labels. The familiar continuum might be an approximation, the way temperature is an approximation of molecular motion. This is where candidate ideas enter, and we introduce them without pretending they're finished. Each is an attempt to replace the classical singularity with a deeper description, one that remains meaningful when curvature becomes extreme. Each tries to recover ordinary spacetime at large scales, while changing what happens at the smallest ones. String theory starts by changing what the fundamental objects are, and it does so in a way that directly targets short-distance behavior. Instead of point particles, it uses extended one-dimensional strings, which smear interactions over a finite length. Their finite size can soften interactions that would otherwise diverge at short distances, because collisions are not concentrated at a single mathematical point. The theory also requires extra dimensions, which are usually compactified or hidden at low energies, so we do not notice them in ordinary experiments. Historically, the idea of extra dimensions dates back to Kaluza and Klein in the 1920s, who noticed that adding a dimension could unify gravity with electromagnetism in a geometric language. Modern string theory extends that intuition, but the extra dimensions become richer and more constrained. In this picture, gravity is not added by hand, and that fact is one reason the idea has held attention for decades. A massless spin-2 excitation of the string behaves like the graviton, and the consistency of the quantum theory forces that mode to be present. Quantum consistency pushes the theory toward a unified framework that includes gauge forces and matter, at least in principle, and it suggests that gravity and quantum mechanics are not strangers. The hope is that the extended nature of strings prevents the infinite curvature of a point-like collapse, because the theory resists being probed below its characteristic length. There is also a web of dualities, equivalences between apparently different descriptions, that hints the smallest distances might be mirrored by large ones. In some contexts, trying to shrink a radius further simply returns you to an equivalent large radius picture. String theory also suggests new early universe possibilities, and these possibilities are not decorative details. There can be branes, higher dimensional objects that can collide or separate, and those interactions can mimic a hot beginning without a classical singularity. There can be transitions that look like a beginning from one perspective, but like a reshuffling of degrees of freedom from another. These ideas hint that what looks like a beginning might be a transition between equivalent descriptions, where before and after are not separated by an infinite barrier. Yet the details are subtle, because one must still recover the observed near uniformity and the measured spectrum of primordial fluctuations. The early universe is not just any high-energy system, is a system with a very specific observational fingerprint. Loop quantum gravity takes a different route, and its starting point is almost the opposite of strings. It keeps the spirit of general relativity, but quantizes geometry directly, treating the gravitational field as a quantum field without assuming a fixed background. Areas and volumes become discrete spectra, like energy levels in an atom, and the continuum becomes an emergent approximation. Spacetime is built from spin networks, combinatorial structures encoding quantum geometry, where links and nodes carry quantum numbers. The visual is striking, not a smooth fabric, but a web of relations whose large-scale limit can resemble a manifold. In this approach, the grain of space is not made of little cubes, it is made of quantized geometric information. In some loop-inspired cosmological models, the Big Bang singularity is replaced by a bounce, and the replacement is not merely poetic. As density approaches a critical value, quantum geometry produces an effective repulsion, which can be understood as a modification of the classical Friedmann dynamics. Contraction can transition into expansion without infinite curvature, and the equations remain finite through the turnaround. The details depend on approximations, because reducing the full theory to a cosmological setting is technically delicate. Yet the core claim is clear, and it is conceptually clean. The classical singularity is not inevitable once geometry is quantized. If the fabric has a smallest meaningful scale, then the classical blow-up is an artifact of treating it as infinitely divisible. Causal set theory and related approaches begin with causality rather than geometry, and they take seriously the idea that before and after might be more fundamental than left and right. They propose that space-time is fundamentally discrete, made of elementary events ordered by causal relations. Volume emerges from counting, and distance emerges statistically, like a macroscopic property of many microscopic elements. Smooth space-time becomes an approximation, like a fluid description emerging from molecules, and that analogy is more than a metaphor. A fluid has no meaning at the scale of a few molecules, yet it becomes an excellent description when you zoom out. Causal set ideas ask whether the manifold is like that. Useful, accurate and emergent, but not fundamental. Other emergent space-time ideas push even further, and they challenge the instinct that geometry must be primary. They suggest that space-time is not fundamental at all, but arises from entanglement patterns or information-theoretic constraints, where connectivity is coded in correlations. In those pictures, the beginning is not a first moment in time, but the onset of a regime where spacetime becomes a useful, effective description. Across these frameworks, a recurring image appears, and it persists because it captures a shared expectation. At Planck scales, spacetime may behave like a quantum foam, where the metric fluctuates violently, and the notion of a fixed background dissolves. Even topology might change, meaning the connectivity of space could fluctuate, so that what counts as one region versus two regions becomes uncertain. Quantum foam is not a single theory, and it should not be mistaken for a completed model. It is a name for the expectation that quantum uncertainty applies to geometry, and that the vacuum of gravity is not empty in the classical sense. If distances fluctuate, then location becomes fuzzy, and if causal structure fluctuates, then the ordering of events can become probabilistic. For a narrator, the visual language matters, because foam is something we can picture. We imagine a dark field where the grid lines of space flicker, and where tiny bubbles of curvature appear and vanish before a camera could even focus. We imagine rulers that bend as they are placed, and clocks that cannot agree on the duration between two flashes. This is where the documentary's central question becomes sharper, because language itself begins to strain. Did anything exist before the Big Bang, and what could it have looked like when space and time were not yet classical? If the smallest scales are foamy, then before may not refer to a clean timeline, and it may not even be a meaningful coordinate. It may refer to a deeper description that does not use time the way we do, where change is encoded in correlations rather than in a universal ticking parameter. When we ask what happened first, we may be importing a macroscopic intuition into a regime where the ordering of events is not fixed. The question becomes not only physical, but also grammatical. What does "was" mean without classical time? Yet even if quantum gravity removes the singularity, it inherits another problem, and this one is not optional. Any pre-Big Bang story must confront the arrow of time, because our universe has a strong thermodynamic direction from low entropy past to higher entropy future. The early universe appears extraordinarily low entropy compared to what gravity allows, and that fact is as observational as the cosmic microwave background. This is not the same as being hot and dense, and the difference is easy to miss. A hot gas can be high entropy for its microphysics, because many particle arrangements look similar at macroscopic scales. But when gravity is included, a smooth, nearly uniform universe is special, because gravity rewards clumping with more available microstates. Clumped matter and black holes represent far higher gravitational entropy, and this is not just a philosophical claim. Black holes have an entropy proportional to the area of their horizons, and for a given mass they can dominate the entropy budget of a region. A universe that begins smooth is a universe that begins in an unusually constrained gravitational configuration. So the mystery is not only why the universe was hot, but why it was so smooth, so ordered, and so close to a particular kind of simplicity. That low entropy condition is what makes time's arrow possible, because it creates room for entropy to increase. Without it, there is no clear sense of past and future, even if the microscopic equations are time-symmetric. The thought is unsettling because it suggests that the beginning is not merely a high-energy event, but a special boundary condition. Why should the universe start in a state that is so atypical among the states gravity permits? Is that specialness explained by dynamics, by selection, or by a deeper principle we have not yet recognized? Some proposals try to explain the arrow by making the low-entropy state generic in a larger setting, where what looks special locally is typical globally. Others propose a two-sided time, where entropy increases away from a central bounce in both directions, so each side sees the other as past. Some treat the arrow as emergent from coarse graining and quantum measurement, where information loss in practice creates an effective direction. None of these answers is settled, and the problem is a constraint, not an optional philosophy. Any model that replaces the singularity must still reproduce the thermodynamic facts we observe, including the remarkable uniformity of the early plasma and the later growth of structure. The arrow is not an afterthought, it is part of the data. The singularity question and the arrow question are linked, and the link tightens as we refine the story. If the beginning is replaced by a bounce or a transition, we must still explain why the post-transition universe begins in such a special macro state. If time emerges, we must explain why it emerges with a direction, rather than as a reversible bookkeeping parameter. A complete origin story must explain both geometry and thermodynamics, and it must do so without hiding behind undefined words. It must say what replaces the singular point, and it must say why the replacement does not erase the arrow we live inside. That is a high bar, and it is the reason so many elegant sketches remain incomplete. At this point, it is easy to drift into unfalsifiable storytelling, because the beginning is a tempting canvas. So we set a rule again. We judge these ideas by what they could leave behind, because science advances when speculation is forced to meet measurement. Quantum gravity is hard to test because the relevant energies are enormous, and the relevant distances are absurdly small. We cannot build a Planck energy collider, and we cannot directly image Planck-length structure with any conceivable telescope. But the early universe is a natural amplifier because tiny quantum features can be stretched to cosmic scales by expansion. Inflation, if it occurred, is the most dramatic example of that amplification, because it can take microscopic fluctuations and blow them up to astronomical wavelengths. Even without committing to a particular inflationary model, the logic remains. Early time physics can imprint patterns on the sky. The universe becomes a detector, and we become the analysts reading its output. One possible imprint is a modified primordial power spectrum, which is the statistical fingerprint of initial density perturbations. Quantum gravity corrections could tilt the spectrum slightly, add running, or introduce features at large scales that deviate from simple slow-roll expectations. Some models predict oscillations or cutoffs that would show up as subtle anomalies in the largest angular modes. The cosmic microwave background is already precise enough to constrain many such changes, and its maps are not just pictures, but data sets with millions of measured correlations. The peaks in its angular power spectrum encode acoustic physics from the early plasma, and the overall shape encodes the primordial seed spectrum. When we talk about testing beginnings, this is one of the primary arenas. Another imprint is non-Gaussianity, which asks whether the primordial fluctuations were purely random in the simplest sense. If the initial fluctuations were generated by non-trivial interactions, their statistics would deviate from a simple Gaussian field, and higher point correlations would carry information. Different shapes of non-Gaussianity point to different mechanisms, and the shapes can be compared directly with data. Current limits are tight, which already rules out broad classes of exotic early dynamics, and that is a quiet triumph. It means the universe, at least in the observable patch, began with fluctuations that are remarkably simple and close to Gaussian. Any quantum gravity scenario that produces large non-Gaussianity must either be tuned or be wrong. Cosmic strings remain a concrete target, partly because they are conceptually clean and observationally distinctive. Some high-energy theories predict string-like defects that could survive and seed gravitational effects, acting like thin lines of trapped energy. They could leave line discontinuities in CMB maps, lensing signatures where images are doubled without distortion, or a stochastic gravitational wave background with a characteristic spectrum. Observations strongly constrain them, but the search continues because a detection would be unmistakable, and it would connect cosmology to fundamental theory in a direct way. A single confirmed string signal would be a relic from energies far beyond terrestrial experiments. It would be a fossil, not of life, but of symmetry breaking in the early universe. Gravitational waves are the most direct messenger from the earliest times, because they interact so weakly that they can travel almost unimpeded. A primordial background could encode the expansion history before recombination, and possibly before inflation ends, in a way that light cannot. Different scenarios predict different spectral shapes across frequency bands, and each band corresponds to a different epoch. Pulsar timing arrays probe nanohertz frequencies, where supermassive black hole binaries create a strong foreground, but where primordial components could hide. Space-based detectors will probe millihertz frequencies, where early universe phase dynamics could contribute, and ground-based detectors probe tens to thousands of hertz. CMB polarization probes even lower frequencies, where inflationary tensor modes would leave a B-mode pattern. Even here, humility is required, because the universe is noisy and the instruments are imperfect. Astrophysical foregrounds can mimic primordial signals, and systematics can masquerade as discovery if the analysis is careless. Many quantum gravity effects could be too small or too degenerate with simpler explanations, and nature is not obligated to provide a clean signature. Still, the effort is not blind, and it is not merely philosophical. The goal is to narrow the space of viable beginnings, using data as a filter rather than as decoration. Each new constraint tells us which kinds of prehistories are compatible with the sky we see, and which are squeezed into corners of parameter space. Evidence is hard but not impossible, and cosmology advances by turning metaphysics into statistics. A model that cannot, even in principle, leave an imprint is not a scientific explanation of our universe, because it cannot be distinguished from its alternatives. The discipline here is not pessimism, it is the method that keeps wonder tethered to reality. As we move closer to the supposed beginning, the universe looks less like a place, and more like a set of probabilities constrained by symmetries and consistency. The classical picture of a point in space and a moment in time becomes a limit of language, useful at human scales but unstable under extreme magnification. The deeper description may be relational, discrete, or emergent, and in every case it forces us to rethink what exists means. This is the narrative tension at the heart of the chapter, and it is also the intellectual tension at the heart of modern cosmology. The closer we get to the origin, the more the word where loses meaning, because location presumes a stable geometry. The closer we get, the more when becomes a property that must be derived, not assumed, because time presumes a stable causal order. The singularity is the point where our intuition runs out before reality does, and that is why it is so productive. It is a failure that points, like an arrow, toward a deeper framework. The question is not whether the universe is strange at the beginning, but what kind of strangeness remains consistent with everything we have measured since. We end this chapter with a practical pivot. If the singularity is replaced, one possibility is that the universe did not begin at all, at least not in the naive sense of a first instant. The word begin might describe the start of our expansion, not the start of existence. A bounce is one of the simplest replacements to state, and it is simple enough to picture even when the physics is not. The universe contracts, reaches a minimum size or maximum density, then expands, and the turning point is governed by quantum gravity effects rather than classical collapse. Time continues through the transition, but the classical description changes near the middle, like a bridge that must be rebuilt to cross a canyon. The pre-Big Bang universe could be older than our expansion, yet still hidden behind a quantum gravity veil, because information might not pass cleanly through the highest curvature regime. Or it might pass in a distorted form, leaving only statistical traces, like a melody remembered after a dream. The key question becomes what survives the bounce and what is erased. In the next chapter, we follow that possibility carefully, because it is both daring and testable in principle. We ask what a bounce would need to reproduce, and what it would change, so that it still matches the cosmic microwave background and the growth of structure. We look for the signatures that could survive a turnaround in time's story, and we test whether the universe could carry a memory of a previous phase. Before the first atom, before the first light, before space had a single direction to point in, what was the universe actually like, and can before even mean anything at all? We use the word before, as if time were a road with mile markers. Yet near the Big Bang, the road itself may be built from quantum rules. If space-time is emergent, then earlier could be a derived concept, not a primitive one. Still, physics is stubbornly practical, and it asks what equations predict when we push them to extremes. Chapter 3 left us at a boundary where classical gravity predicts a singularity and stops. In general relativity, a singularity is not just a large number on a graph. It is a breakdown of the theory's ability to describe distances, clocks, and causal structure. The Hawking, Penrose singularity theorems formalize this tension. Under reasonable energy conditions, geodesics end in finite proper time. That conclusion is mathematical, but its meaning is physical. Classical spacetime becomes incomplete. A bounce proposal takes that warning seriously and replaces the singularity with a transition. The Big Bang becomes a rebound from contraction, or a passage from one phase to another. The core idea is simple to state and hard to make consistent. The scale factor shrinks, density rises, and quantum effects prevent infinite curvature. Instead of an infinite spike, the universe reaches a minimum size or maximum density, then re-expands into the hot phase we reconstruct. In the usual hot Big Bang picture, temperature tracks the scale factor like an inverse power, so contraction implies heating. As the volume compresses, particle energies climb, interactions intensify, and the notion of a smooth fluid can fail. A successful bounce must therefore do more than avoid infinity. It must guide the universe through a regime where both geometry and matter are stressed. So we set a rule. Any bounce must reproduce the evidence we already trust, including nucleosynthesis and the CMB's precise statistics. That rule sounds modest, but it is demanding in practice because the early universe is tightly measured. Big Bang nucleosynthesis locks in the expansion rate when the universe was seconds to minutes old. The cosmic microwave background locks in the perturbation pattern when the universe was about 380,000 years old. Between those anchors, the model must deliver a radiation-dominated universe with the right thermal history. A bounce is attractive because it offers continuity through time without a first instant. It can also reframe the horizon and flatness puzzles as inherited conditions rather than miracles. In standard cosmology, widely separated regions of the CMB were never in causal contact without an early smoothing mechanism. A contracting phase can, in principle, allow those regions to interact before the bounce, if the contraction lasts long enough and remains well behaved. If pre-bounce evolution smooths and correlates regions, the CMB's uniformity becomes less mysterious. But the same idea raises a sharper question. What kept the contracting universe stable long enough to do that smoothing? The bounce is not one model, and the differences matter observationally. Some bounces are quantum gravity turnarounds in 4 dimensions, where spacetime itself changes its rules at high density. Others are effective descriptions of higher dimensional dynamics, or of exotic matter phases that behave unlike anything in laboratories. In visuals, these options look similar, one curve down, one curve up. But their microphysics can be radically different. That microphysics determines which perturbations survive, which are amplified, and which are erased. Loop quantum cosmology is the most explicit quantized geometry bounce in common discussion. Its roots trace to loop quantum gravity, a program developed in the late 20th century to quantize general relativity without assuming a fixed background. Instead of quantizing small ripples on a pre-existing spacetime, the approach tries to quantize geometry itself, It starts from the claim that geometric quantities have discrete spectra, much like energy levels in atoms. Areas and volumes behave like quantized observables, not infinitely divisible continua. In the imagery, space becomes a network of links and nodes, an evolving weave rather than a smooth fabric. In LQC, the Friedmann equation is modified at extreme density. Classically, the Hubble parameter squared is proportional to the energy density, so higher density means faster contraction or expansion. In LQC's effective equations, that relationship gains a correction that becomes important near a critical density. The correction acts like repulsive gravity when the density approaches that critical value, often near the Planck scale. Contraction slows, the Hubble parameter crosses through zero, and expansion begins again. The turnaround is not an arbitrary patch. It is a consequence of the modified dynamics in the high curvature regime. Conceptually, the repulsion is not a new force added by hand. It is an effective consequence of quantum geometry, where the classical connection variables are replaced by holonomies. Holonomies encode curvature through finite loops, so the theory avoids taking arbitrarily small limits that would probe an assumed continuum. That discreteness changes how curvature contributes to dynamics at small scales, and it softens the classical divergence. A useful plain language analogy is that the theory refuses to let space-time be compressed without bound. But the analogy has limits, because the stiffness comes from quantum kinematics, not from a material substance. The payoff is a non-singular evolution that can be extended through the would-be beginning. Time does not end at a point of infinite curvature in the effective description. The pre-bounce branch becomes a legitimate part of the space-time history, at least within the symmetry assumptions used. In a visualization, the scale factor curve approaches a minimum and turns upward smoothly, while curvature peaks and then declines. Temperature climbs during contraction, reaches a maximum, and then falls as expansion resumes. The Big Bang becomes a hot crossing rather than a creation event, yet LQC inherits immediate questions about initial conditions and robustness. The bounce occurs in highly symmetric settings that simplify the full quantum theory, often assuming homogeneity and near isotropy. Those assumptions are not cosmetic, because anisotropy and contraction can behave like a runaway instability. The challenge is whether inhomogeneities and anisotropies remain controlled near the turnaround, where small effects can become large. Researchers study perturbations on top of the bouncing background, but the results depend on how one treats quantum fluctuations of geometry. Even the definition of a vacuum state can shift predictions, because there is no unique time translation symmetry near a bounce. A second family is ekpyrotic and cyclic cosmology, often motivated by branes and extra dimensions. The term ekpyrotic comes from an ancient Greek word for a cosmic conflagration, hinting at a hot transition after a long prehistory. Historically, these models rose in the early 2000s as alternatives to inflation, partly inspired by developments in string theory. Here the Big Bang can be a collision or close approach of branes, seen as a hot transition in 4 dimensions. The before is a long, slow contraction, rather than a rapid early expansion. In visuals, 2 vast sheets drift in a higher dimensional space, their approach compressing the effective universe we inhabit. Ekprosis is defined by an ultra-stiff equation of state during contraction. An equation of state relates pressure to energy density, and stiff means pressure is large compared to density. In this regime, the energy density in the ekpyrotic field grows faster than anisotropies as the universe contracts. In effect, it suppresses the chaotic mixmaster behavior that otherwise dominates contracting universes. The mixmaster picture, associated with Belinsky, Kalatnikov, and Lifshitz, describes a generic approach to a singularity as a sequence of chaotic, anisotropic oscillations. Ekpyrosis tries to replace that chaos with a controlled smoothing contraction, driven by a steep potential energy landscape. This is the key contrast with inflation. Inflation smooths by accelerated expansion that dilutes curvature, defects, and unwanted relics. Ekpyrosis smooths by slow contraction that dynamically drives the universe toward homogeneity and flatness. Both mechanisms are, in a sense, attractors. They make a wide range of initial conditions converge toward a simpler state. But the direction of the attractor in time is reversed, and that reversal changes how perturbations are generated and interpreted. When we watch the CMB map sweep across the screen, the question becomes whether its simplicity was stretched into existence or squeezed into existence. Both approaches aim at the same observational target. They must explain why the universe looks nearly flat, nearly uniform, and seeded with nearly scale-invariant perturbations. Scale-invariant here means that fluctuations have nearly the same strength across a wide range of wavelengths, with only a slight tilt. In inflation, quantum fluctuations are stretched beyond the Hubble radius and later re-enter as classical density variations. In contraction-based models, modes can also exit an effective horizon, but the bookkeeping of growing and decaying modes changes. The difference is the direction of the smoothing process in time, and the mathematical mode evolution remembers that direction. Matter bounce scenarios take a different route for perturbations. They aim to generate the observed spectrum during contraction, often when the universe is dominated by pressureless matter. Pressureless matter has an equation of state close to zero, which changes how the Hubble radius evolves with time. In that phase, curvature perturbations can acquire an approximately scale-invariant spectrum, at least in idealized treatments. The mechanism is appealing because it uses familiar dynamics rather than a special slow-roll potential. Modes exit the Hubble radius during contraction and freeze, then re-enter after the bounce. The Big Bang becomes a handoff between two classical regimes, with the bounce acting as a short bridge between them. But matter contraction has a known instability. Anisotropies typically grow as the scale factor shrinks, faster than ordinary matter energy density. This is the BKL instability, where generic contraction becomes chaotic and anisotropic. In a visual metaphor, the universe stops behaving like a smooth shrinking balloon and starts behaving like a collapsing, tumbling object. Small directional differences in expansion rates amplify, and shear energy can dominate the dynamics. If that happens, the neat perturbation story is overwhelmed by a more violent approach to the bounce. So we set a rule again. A viable bounce must tame anisotropy growth without fine-tuned initial conditions that simply hide the problem. Fine-tuning is not a moral failure, but it is a scientific warning sign when it becomes extreme. If the model works only for exquisitely special initial states, then it risks explaining our universe by assuming it. A good bounce should have a dynamical reason for remaining smooth, not just a carefully chosen starting point. Ekpyrosis is one proposed cure because its ultra-stiff component dominates anisotropies. Some matter bounce models add an ekpyrotic phase before the bounce to suppress BKL growth. Others invoke modified gravity or special matter that violates energy conditions safely, at least within an effective theory. That phrase, violates energy conditions, is where many bounces become fragile. In classical general relativity, a bounce in a flat universe often requires violating the null energy condition, which roughly states that energy density plus pressure is non-negative along light-like directions. Violating it can allow the Hubble parameter to increase through zero, but it can also introduce ghosts or gradient instabilities. A ghost is a degree of freedom with negative kinetic energy, and it tends to make the vacuum catastrophically unstable. A gradient instability can make small spatial fluctuations grow explosively fast, ruining the smooth background. Quantum gravity bounces try to avoid that by changing the gravitational sector itself. Effective field theory bounces often change the matter sector or add higher derivative terms that alter the equations of motion. Either way, stability constraints become as important as the background evolution. A bounce curve on a slide is easy. A bounce that is stable to perturbations is far harder. The model must keep sound speeds physical, avoid superluminal pathologies when possible, and remain predictive below its cutoff scale. The observational question is not whether a bounce can be drawn on a timeline. The question is what information could survive the highest curvature regime. If the bounce scrambles phases or mixes modes, the pre-bounce universe may be unobservable in practice. In quantum language, the issue is whether evolution through the bounce is effectively unitary for the perturbations we measure. In classical language, it is whether the bounce behaves like a clean lens or like turbulent water. Even if the background is smooth, perturbations can experience strong coupling that breaks simple linear calculations. Still, many bounce frameworks predict testable differences from simple inflation. One target is the primordial power spectrum at the larger scales. A bounce can imprint a cutoff, oscillations, or scale-dependent features from matching conditions across the turnaround. Those features often show up at low multipoles in the CMB, where we have fewer independent modes to average over. That scarcity is cosmic variance, and it is a built-in limit rather than an experimental flaw. So the larger scales are tempting, but they are also the noisiest place to claim discovery. Another target is running of the spectral index. The spectral index describes the tilt away from perfect scale invariance, and running describes how that tilt changes with scale. If the spectrum is generated in contraction, the tilt and its running can differ from slow-roll expectations. Small deviations matter because Planck and large-scale structure already measure them tightly. In a plot, the difference can look like a subtle bend in a line, yet that bend encodes the universe's earliest dynamics. Non-Gaussianity is a sharper discriminator. Gaussian fluctuations are fully characterized by their two-point statistics, meaning the power spectrum tells most of the story. Non-Gaussianity adds higher-order correlations, captured by the bispectrum and trispectrum, which act like fingerprints of interactions. Many bounce mechanisms involve non-trivial interactions or mode mixing near the bounce that can produce distinctive bispectrum shapes and amplitudes, sometimes larger than typical single-field slow-roll inflation. But the same interactions that generate strong non-Gaussianity can also threaten perturbative control. The model must produce a signal without producing a breakdown of its own approximations. The constraints are already restrictive. Observations favor nearly Gaussian, adiabatic perturbations with specific phase relations in the acoustic peaks. Adiabatic means different components fluctuate together, preserving relative number densities at early times. Any bounce must reproduce that simplicity without erasing the very signatures it hopes to advertise. It is a narrow target. Too much complexity is ruled out, and too little makes the bounce indistinguishable from inflation. That tension is what makes the subject scientifically interesting rather than purely speculative. Tensor modes are another key difference. Tensor modes are primordial gravitational waves, ripples in space-time that imprint polarization patterns in the CMB. Many bounce models predict low primordial gravitational wave amplitudes at CMB scales. Some produce blue-tilted tensor spectra that shift power to higher frequencies, away from CMB B-mode searches. In inflation, a nearly scale-invariant tensor spectrum is common in simple models, though not guaranteed. In bounce scenarios, the tensor story can be suppressed, reshaped, or shifted into bands where different instruments listen. That changes the experimental strategy. CMB polarization limits already rule out large tensors at low multipoles, tightening the space for high-scale inflation. A bounce could be consistent with that silence while still producing a detectable stochastic background at interferometer or pulsar frequencies. In visuals, the spectrum slides to the right, away from the CMB window, toward the frequency ranges of LIGO-like detectors and pulsar timing arrays. But the same caution applies. Astrophysical foregrounds can dominate those bands, and a primordial signal must be separated by spectral shape and cross-correlation tests. A bounce prediction is only useful if it is distinct enough to survive real data analysis. What survives a bounce is also a question about degrees of freedom. If the bounce is unitary and information-preserving, correlations could pass through in principle. If the bounce involves decoherence, particle production, or strong coupling, the memory could be effectively lost. Particle production is not an exotic add-on. In curved space-time, changing backgrounds can create quanta from vacuum fluctuations. If that creation is violent near the bounce, it can back-react on the geometry and alter the very dynamics that produced it. The bounce then becomes a coupled system, not a simple background with small passengers. Some LQC discussions suggest certain perturbation variables evolve smoothly through the bounce. Others emphasize that the choice of vacuum and matching prescription can change predictions. The uncertainty is not cosmetic because it changes what testable means. If different reasonable choices yield different spectra, then the model must supply a principle that selects among them. Otherwise, the bounce risks becoming a menu rather than a prediction. The deeper question is whether the quantum state of geometry itself should be treated as a measurable input or as a derived outcome. Ekpyrotic models face their own perturbation challenge. A single ekpyrotic field tends to produce a blue spectrum for curvature perturbations, meaning too much power on small scales. Many versions therefore use entropic perturbations in multi-field setups, then convert them to curvature perturbations later. Entropic perturbations are fluctuations orthogonal to the background trajectory in field space, and they can be nearly scale invariant during ekpyrotic contraction. The conversion can occur through a bend in the trajectory, a feature in the potential, or a dynamical instability that transfers power. That conversion can generate non-Gaussianity and isocurvature signatures. Observations strongly limit isocurvature modes in the CMB, so the model must convert efficiently while leaving the final perturbations predominantly adiabatic. Cyclic versions add another layer of ambition. They propose repeated phases of expansion and contraction, with bounces connecting cycles. The Big Bang becomes one event in an endless sequence rather than a unique origin. In a time-lapse visualization, galaxies form, drift apart, fade, and then the cosmic scale reverses, compressing toward another transition. The story becomes rhythmic, but physics immediately asks what keeps the rhythm stable. This raises the entropy problem immediately. In ordinary thermodynamics, entropy increases and cycles would accumulate disorder. Entropy is often described as disorder, but more precisely it counts the number of microscopic configurations compatible with a macroscopic state. If entropy grows each cycle, the cycles cannot be identical forever. The universe would carry a memory of past cycles in the form of accumulated radiation, black holes, and irreversible processes. Even if the geometry repeats, the contents would not, and the arrow of time would not reset by itself. Some cyclic proposals respond by making each cycle larger than the last. Expansion can dilute entropy density, even if total entropy increases, so each new cycle begins emptier per unit volume. But that means the cycles are not truly periodic, and the past becomes a sequence of ever smaller cycles. In that picture, eternal does not mean uniform repetition. It means an infinite chain with changing scale. The visual implication is striking. The further back you go, the smaller and shorter the cycles become, like nested ripples. Other proposals try to reset entropy through mechanisms tied to horizons, dilution, or the shedding of entropy into regions that become causally disconnected. These ideas are controversial and model-dependent because they rely on global structure that is hard to define operationally. They also force us to define what counts as the same universe, across cycles. If entropy is pushed beyond a horizon, is it gone, or is it simply elsewhere in a larger spacetime? If it is elsewhere, then the cycle did not erase entropy, it relocated it. The distinction matters because it determines whether the model explains the arrow of time or merely hides it. The arrow of time becomes a central constraint, not a philosophical add-on. Our universe shows a strong thermodynamic direction from low entropy past to higher entropy future. That direction is visible in everything from the cooling of stars to the formation of structure and the irreversibility of chemical reactions. A bounce must explain why the post-bounce state is low enough entropy to allow the arrow we observe. If the bounce emerges from generic high entropy contraction, then why does it produce a special low entropy beginning afterward? This is one of the deepest pressures on any earlier universe narrative. One possibility is a two-sided arrow. Entropy increases away from the bounce in both time directions, so observers on either side call the bounce the past. That makes the bounce a kind of temporal mirror, not a beginning. In visuals, the entropy curve forms a V-shape, with the minimum at the bounce and growth on both sides. It is an elegant idea, but it demands a special low entropy condition at the bounce itself. The question then shifts from why a beginning to why a minimum, and the mystery does not disappear. But that picture collides with what we mean by memory and causation. If both sides see entropy increasing away from the bounce, then what does it mean for information to pass through? Records are physical, and they require stable correlations stored in low entropy structures. If the bounce is the entropy minimum, it may also be a bottleneck for such records. The bounce could be a boundary for memories, even if it is not a boundary for equations, so the universe might be continuous in a mathematical sense while still being discontinuous in an observational sense. There is also the question of what sets the pre-bounce phase in the first place. A bounce gives a before, but it does not automatically give an explanation. We still have to ask why the universe was contracting and why it reached the conditions that trigger a rebound. In some models, contraction is part of a larger solution space, and our branch is one trajectory among many. In others, contraction requires a specific potential, a particular matter content, or a boundary condition imposed at infinity. The bounce can move the mystery, not remove it, and that relocation is part of the honest accounting. A deeper mystery is whether the laws are the same across the bounce. If there was a previous universe, did it share our constants and particle content? Or could the bounce act like a reset, changing effective couplings or vacuum states? In quantum field theory, what we call constants can depend on vacuum expectation values and on the configuration of hidden fields. If those fields evolve through the bounce, then the effective low-energy laws could differ on either side. The bounce would then be not just a geometric event, but a kind of cosmological selection step. In LQC-style bounces, The underlying quantum geometry is usually taken as fixed. The constants are assumed to be the same on both sides, and the bounce is a dynamical event within one theory. But even there, the choice of quantum state can affect effective parameters, such as the precise value of the critical density. Different semi-classical states can lead to slightly different effective trajectories, and those differences can propagate into perturbation predictions. So, same laws may still allow different realized histories, depending on the state of the quantum geometry. In brane and string-motivated bounces, the possibility of changing moduli is harder to ignore. Moduli describe the shapes and sizes of extra dimensions, and they influence the couplings and masses we measure in 4 dimensions. Extra-dimensional shapes can shift, and effective 4-dimensional constants can vary between phases. That raises the prospect of cosmological inheritance, rather than strict repetition. A previous phase might pass down a spectrum of fluctuations while also altering the parameters that govern how those fluctuations evolve afterward. It is continuity with a twist, like a story retold with different rules of grammar. If constants can change, the observational consequences become subtle. We would not see the previous constants directly, but we might see relic features in the spectrum or relic defects. We might also see statistical anomalies that suggest a non-standard prehistory, though anomalies are notoriously hard to interpret. A small suppression of power at large scales, a phase shift in oscillations, or an unusual bispectrum shape could be hints, but each hint must compete with mundane explanations like foregrounds, systematics, and the limited number of large-scale modes. The universe does not hand us clean labels that say pre-bounce, yet the same flexibility can become a weakness. If the bounce can adjust constants freely, it risks becoming unfalsifiable. A scientific bounce must restrict its own freedom enough to make sharp predictions. That restriction can come from symmetry principles, from consistency conditions like the absence of ghosts, or from embedding in a broader theory with limited parameters. Without those constraints, the bounce becomes a narrative that can fit anything after the fact. So we set a rule one more time. We treat a bounce as a hypothesis about measurable relics, not as a license to invent an untestable earlier universe. This rule is less about skepticism and more about discipline. Cosmology has a history of bold ideas that became science only when they met data, from the expansion of the universe to the existence of the CMB. A bounce must earn the same status by confronting observations, not by avoiding them. There are specific places to look for bounce fingerprints. The largest angle CMB anomalies are one tempting arena because they probe the biggest wavelengths and earliest horizon exit. In the sky map, these are the broad, gentle gradients and low multipole patterns that span huge fractions of the celestial sphere. But cosmic variance limits certainty there, so claims must be cautious. A model that relies entirely on low-L anomalies is leaning on the least statistically robust part of the data. Still, if a bounce predicts a distinctive cutoff or oscillation phase, even a weak hint can motivate targeted tests. Large-scale structure provides another arena. Features in the primordial spectrum propagate into the matter power spectrum and into BAO reconstruction. Galaxies trace the underlying dark matter field imperfectly, but surveys can still test for oscillatory features and scale-dependent bias. As the camera flies through a 3D galaxy map, filaments and voids become a fossil record of early fluctuations. Departures from simple power law initial conditions can leave subtle ripples in clustering statistics. The advantage is volume. Large surveys measure many modes, reducing statistical noise compared to the CMB's larger scales. Primordial black holes can also act as constraints or signals. Some bounce models enhance power on small scales, which can overproduce black holes when overdensities collapse after horizon re-entry. Non-detection in certain mass windows becomes a limit on bounce dynamics, because too much small-scale power is not allowed. The constraints come from lensing, from gravitational wave merger rates, from CMB distortions, and from the survival of astrophysical systems. In this way, even silence becomes data, narrowing the allowed behavior of the bounce near its most extreme moment. Gravitational waves remain the most direct messenger of extreme early behavior. A bounce can produce a spectrum from amplification of vacuum tensor modes, from phase transitions, or from anisotropic stress near the turnaround. The predicted tilt and amplitude can differ strongly from inflation, especially if the spectrum is blue and rises toward high frequencies. In visuals, the wave background becomes a shimmering field, with intensity shifting across frequency bands like a moving spotlight. But interpretation is unforgiving. astrophysical backgrounds from compact binaries can mimic a stochastic signal, so the primordial component must be identified by its spectral slope and consistency across detectors. But the bounce must also pass the simplest tests. It must deliver the correct light element abundances by the time nucleosynthesis begins. It must deliver a universe that thermalizes into the hot plasma whose acoustic oscillations we measure. Thermalization is not automatic, because a bounce can leave the universe in an unusual state with non-standard particle populations. If reheating is inefficient or delayed, the radiation era begins too late, and BBN predictions fail. So the bounce must connect to standard radiation domination quickly and cleanly, with the right number of relativistic degrees of freedom. That requirement forces the bounce to connect to standard radiation domination quickly and cleanly. Any exotic component that lingers can change expansion rates and spoil BBN. The early universe is a narrow corridor, and the walls are observational. Even small changes in the Hubble rate alter neutron-to-proton freeze-out and shift helium and deuterium yields. The corridor metaphor is literal in parameter space. Many bounce models are squeezed into thin, viable regions by existing measurements. A bounce also has to address the homogeneity problem without hiding fine-tuning. If contraction begins with significant inhomogeneity, it can form black holes and fragment before any smooth bounce occurs. In a contracting universe, overdensities grow quickly, and the time available for collapse can be short. The smoothing mechanism must be strong enough to be plausible, not just mathematically possible. Ekpyrosis is designed for that, but it requires a specific steep potential and a controlled conversion to curvature perturbations. LQC provides a bounce mechanism, but it still needs a story for perturbations and for the arrow of time. Matter bounces generate spectra naturally, but they fight anisotropy and stability. The comparison is not about picking a winner, it is about mapping trade-offs, because each framework solves one set of problems by paying another cost. A model that elegantly removes the singularity may struggle with perturbations. A model that generates the right spectrum may require delicate control of instabilities. A model that smooths contraction may complicate non-Gaussianity or isocurvature constraints. The documentary question is whether any cost is paid in a way that leaves a detectable trace. If the price is paid invisibly, then the bounce becomes a metaphysical preference rather than an empirical theory. At this point, the bounce idea changes the emotional shape of the story. It offers a before that feels like a recovered chapter, a continuation rather than an abrupt start. The visuals invite it, a universe contracting like a slow inhale, then expanding like an exhale into fire and light. But it also forces a deeper question about why there was a pre-bounce chapter at all. Continuity is comforting, yet it does not automatically provide explanation. It replaces the mystery of a first moment with the mystery of a particular trajectory through possibility space. If the universe can bounce, why did it ever contract into a bounce-ready state? If it bounces repeatedly, why does the arrow of time not wash out across cycles? If it bounces once, what selects that history among other quantum possibilities? These questions are not rhetorical decoration, because they point to what the model must ultimately specify. A bounce is a mechanism, but a cosmology is a mechanism plus a measure over histories, an account of what is typical. Without that account, we do not know whether our universe is expected or exceptionally rare. We end this chapter with a practical pivot. A bounce suggests continuity through time, but inflation suggests something else, the possibility of many beginnings. Inflation, in many versions, does not merely smooth a universe, it can also generate self-reproducing regions through quantum fluctuations of the inflaton field. In that picture, our beginning is one bubble or patch among many, each with its own initial conditions and perhaps its own effective parameters. The contrast is sharp. The bounce asks what came before, while inflation can ask how many starts occur. The next step is to confront that alternative directly. If inflation can erase prehistory, it can also generate a multiverse of outcomes. The question shifts from what came before to how many beginnings can physics allow? And at the threshold where time and space may dissolve, before the Big Bang becomes less a place in history and more a test of what reality is made of, an invitation to replace certainty with better questions, and to let evidence, not intuition, decide what the beginning truly means. Before the first atom, before the first light, before space had a single direction to point in, what was the universe actually like? And can before even mean anything at all? Even the grammar starts to wobble here, because before assumes time already exists and flows. When cosmologists talk about the earliest moments, they are really talking about limits of description, where our equations still behave and where they begin to fail. So the question becomes two questions at once. What does our best physics imply, and what does it leave undefined? Inflation began as a fix for puzzles that looked like coincidences in the hot Big Bang. In the late 1970s, the standard Big Bang picture was already successful, yet it carried several awkward initial conditions that seemed unnaturally tuned. Why is the universe so close to spatially flat, balanced as if it were set on a knife edge? Why is the cosmic microwave background so uniform across regions that, in a simple expansion, were never in causal contact? And why do we not see heavy relics, magnetic monopoles and other exotica that many high-energy theories seem to predict? Inflation proposed a single dynamical phase that could make those coincidences look like outcomes of expansion rather than miracles of initial setup. In the simplest picture, a field called the inflaton sits on a high-energy plateau. A field here is not a substance you could scoop up. It is a value assigned to every point in space, like temperature on a weather map. If that field's potential energy dominates, its energy density stays nearly constant even as space grows. That behavior mimics a temporary vacuum state, and it produces a peculiar kind of gravity, repulsive in its large-scale effect. General relativity translates that vacuum-like energy into accelerated expansion, meaning the scale factor grows faster and faster with time. Its energy behaves like a temporary vacuum, driving accelerated expansion that stretches space faster than light can cross it. This does not violate relativity, because nothing locally outruns a light beam through space. Instead, the distance between faraway points increases because the metric, the ruler of space-time itself, is changing. Light still follows local null paths, and particles still obey causal limits in their neighborhoods. Yet the global separation between regions can grow so quickly that signals can never catch up across the swelling geometry. That expansion is not a normal explosion into pre-existing emptiness. A conventional explosion has a center and an edge, and it expands into space that was already there. Inflation is different. Space is what is expanding, and every location can see itself as the center. If we could visualize it, we would not draw a fireball pushing outward. We would draw a grid whose squares balloon in size while the inclines remain locally well-behaved. The universe becomes smoother as it expands because curvature and unwanted relics are diluted like a drop of dye in an ocean. Inflation also turns quantum noise into cosmic structure. In quantum field theory, empty space is not truly empty. It seethes with fluctuations constrained by the uncertainty principle. Even in a vacuum state, fields jitter around their average values, producing temporary variations in energy and amplitude. During inflation, those microscopic jitters are stretched to astronomical scales, and their wavelengths can exceed the horizon. When a mode freezes outside the horizon, its pattern becomes imprinted as a classical-looking perturbation in the density. Later, as the universe expands more slowly, those modes re-enter the horizon and begin to influence matter and radiation. They become the seeds of galaxies, clusters, and the web-like structure that telescopes map across billions of light years. But the twist is that quantum fluctuations do not only perturb density, they can also perturb the inflaton field itself, changing when inflation ends from place to place. This is the subtle step that turns inflation from a one-time smoothing event into a potential generator of many beginnings. To see why, we have to picture the inflaton not as a single number, but as a landscape of values across space. Most of the time, the field rolls downhill, but quantum mechanics adds a random component, small kicks that can push it around. In many models, the inflaton rolls downhill toward a lower energy state. Classically, it would end everywhere at nearly the same time, because the field would follow the same deterministic equation of motion. That classical motion is often described by slow roll, where friction from expansion damps the field's acceleration. The inflaton drifts down its potential as the universe inflates, and the inflationary phase ends when the field reaches a region where vacuum-like energy no longer dominates. In that classical picture, the end is almost synchronized, like a curtain falling across an entire stage. Quantum mechanics adds randomness to that roll. In some regions, the field fluctuates upward enough to delay the end, even while neighboring regions keep rolling down. The key competition is between two rates: how fast the field classically rolls downhill and how large the quantum kicks are per Hubble time. If the quantum step size is comparable to, or larger than, the classical drift over the same interval, then some patches will climb upward. Those upward fluctuations are rare, but inflation rewards rarity with volume, because regions that keep inflating expand exponentially. If the upward kicks happen often enough, inflation becomes self-reproducing. Space expands so quickly that regions still inflating outgrow the regions that have ended. Even if most patches eventually roll down and stop, the remaining inflating patches can produce more physical volume than all the stopped patches combined. The result is a runaway process. Inflation never ends everywhere at once, because there is always some region where it continues. This is the sense in which inflation can be eternal, not eternal in each location, but eternal in the global mosaic. So inflation can be eternal to the future, even if it ends locally. The global space-time keeps inflating somewhere, while pockets stop and become hot universes. If we could pull back far enough, the picture would resemble a dark, swelling background punctuated by glowing islands. Each island is a region where inflation has ended, where energy is converted into particles, and where time begins to look like our familiar cosmic history. Between islands, the inflating space keeps stretching, thinning, and erasing traces of what came before. The background is not a place you could travel to. It is a dynamical regime that keeps generating new places. Those pockets are often described as bubble universes. Each bubble is a region where the inflaton has fallen into a lower energy vacuum and inflation has shut off. The word bubble is visual shorthand, but it captures an important feature. The boundary is a transition surface between two phases. In many models, bubbles form by quantum tunneling, like a metastable state decaying to a more stable one. A useful analogy is supercooled water suddenly crystallizing, except here the phase is a vacuum state of fields. Once nucleated, the bubble wall accelerates outward, and the interior becomes a new expanding universe with its own thermal history. Inside a bubble, the story looks familiar again. The vacuum-like energy that drove inflation is converted into ordinary particles and radiation. This conversion is reheating, and it is the local trigger for a hot Big Bang phase. The Big Bang becomes a regional event, not the start of everything. That shift is easy to say and hard to absorb, because it demotes our beginning to a boundary condition inside a larger process. It suggests that what we call the Big Bang may be more like the ignition of a furnace than the creation of the room. Reheating is not a metaphorical spark. It is a physical process where the inflaton's energy decays into a hot plasma of quanta that can thermalize. Depending on the model, the inflaton can oscillate around the minimum of its potential and transfer energy to other fields. That transfer can occur through perturbative decays or through explosive, nonlinear processes often called preheating. Either way, the end state is a bath of particles with a temperature set by how efficiently energy is dumped into the standard model sector. Thermalization is crucial because it erases detailed memory of the inflaton's microstate and produces the smooth, hot initial conditions used by Big Bang calculations. Once reheating happens, standard cosmology can begin. Radiation domination follows, with energy carried mostly by relativistic particles, and the expansion rate set by well-tested physics. As the universe cools, protons and neutrons form and interconvert, and light nuclei are synthesized in the first minutes. Hundreds of thousands of years later, electrons combine with nuclei, the plasma becomes neutral gas, and photons decouple. Those photons are the cosmic microwave background, a nearly uniform glow that still fills the sky at 2.7 Kelvin. Every step in this sequence is constrained by observation, which is why inflation must ultimately feed into this familiar thermal story. From inside, the bubble has an apparent beginning. The hot state is the earliest time we can reconstruct with the tools of the hot Big Bang. Our telescopes and detectors do not see behind the reheating surface, because earlier than that there were no atoms, no stars, and no transparent medium for light to cross. We infer earlier conditions indirectly, through the statistics of perturbations and the consistency of cosmic evolution. The beginning is therefore partly epistemic, defined by what can leave traces that survive to the present. That is a sobering thought. The start of our story may be the start of what can be remembered. From outside, if outside is meaningful, the bubble is one outcome among many. The inflating background continues, and new bubbles can keep forming. Yet, outside is a dangerous word, because it suggests a higher dimensional room in which universes float like soap spheres. In the mathematics, the inflating region is just another part of space-time, and the bubble interior is a different part, separated by a dynamical boundary. Still, for visualization, we often imagine a black inflating sea with bright expanding shells. Each shell a local end of inflation, each interior a new thermal cosmos. This reframes the central question in a disturbing way. Maybe there was no single moment when the universe began, only many local beginnings. If so, then the word "the" in the Big Bang becomes misleading, because it implies a unique event. Instead, the Big Bang would be a class of events, repeated across the inflating space-time whenever and wherever inflation ends. We are then forced to ask what we mean by origin, the origin of our region, or the origin of the entire inflating structure. The two are not the same, and the difference matters. Eternal inflation also changes what "before" means. Before our reheating, there may have been inflating spacetime with no hot plasma and no atoms. The physics would be dominated by vacuum-like energy, with quantum fields fluctuating on a rapidly expanding background. Time would still be part of the description, but it would not be marked by familiar milestones like nucleosynthesis or recombination. In that regime, "before" is not a calendar of events, but a different phase of the same underlying dynamics. The universe, in this view, is not born hot everywhere, it becomes hot in patches. Yet inflation is not a complete origin story by itself. It is a dynamical phase that still assumes some underlying laws and some initial condition for the inflaton. We still have to specify why an inflaton field existed, why its potential had the right shape, and why a region began in the right state to inflate. Even the phrase "initial condition" is slippery, because it assumes a prior time on which conditions are set. Inflation can push questions back, and it can change their form, but it does not automatically eliminate them. This is why the multiverse, however seductive, cannot be treated as a free pass on origins. So we set a rule: any multiverse claim must still connect to evidence in our sky, or it remains a philosophical preference. That rule is not hostility but discipline, because cosmology has learned repeatedly that beautiful ideas must submit to data. Inflation itself earned credibility by making contact with observations, especially through the microwave background. If eternal inflation adds a global structure, it must do so without losing the ability to say something testable about our patch. Otherwise, it becomes a narrative that can always accommodate whatever we see, which is another way of saying it predicts nothing. The strongest evidence inflation already uses is the CMB's statistics. The perturbations are nearly scale invariant, adiabatic, and close to Gaussian. Scale invariant means fluctuations have almost the same strength on many length scales, with a slight tilt that matches slow roll expectations. Adiabatic means different components, photons, baryons, dark matter, start with correlated perturbations as if they share a common origin. Gaussian means the fluctuations resemble a random field whose information is mostly contained in the two-point correlation function. These are not vague impressions. They're quantified in the angular power spectrum and higher-order statistics measured by missions like WMAP and Planck. The CMB is a fossil image, and inflation's fingerprints are in its faint mottling. Eternal inflation tries to keep those successes while adding a global structure. It says our observed patch is a typical outcome of a much larger inflating spacetime. In many versions, the local physics inside a bubble can look almost identical to ordinary inflation, because the same mechanism generates perturbations. The difference is not in the local equations, but in the global bookkeeping, how many bubbles form, how they differ, and what observers should expect. That is where the concept of typical becomes both necessary and treacherous. But typical is exactly where trouble begins. Eternal inflation tends to produce infinitely many bubbles, and infinities break ordinary probability. If every allowed outcome occurs without bound, then naive counting cannot tell us what is likely. In a finite ensemble, we can say one outcome happens 60% of the time and another happens 40%. In an infinite ensemble, both can happen infinitely often, and infinite over infinite is not a number until we define a procedure. The multiverse forces probability to become a question of definition, not just measurement. This is the measure problem. If every allowed outcome happens infinitely many times, then counting outcomes does not define a unique probability. The measure is the rule that assigns weights to different regions or histories, telling us how to compare them. Different measures can be motivated by different intuitions. cutting off at a fixed time, or a fixed scale factor, or along certain geodesics. But in an eternally inflating spacetime, these choices can yield different answers, even when they all sound reasonable. That is not merely annoying, it undermines the claim that the framework makes definite predictions. In everyday life, probability is a ratio of counts in a large sample. In an infinite multiverse, the sample is not just large, it is unbounded. Imagine trying to compute the fraction of integers that are even by listing them in different orders. If you list them naturally, half are even, but if you reorder cleverly, you can distort the apparent fraction in partial lists. The multiverse has a similar ambiguity, because how you list the events corresponds to how you slice spacetime and impose a cutoff. The measure problem is, in part, the problem of defining a non-arbitrary ordering for an unending process. To make predictions, one introduces a cutoff, like a time slice or a volume limit. Then one takes the cutoff away and hopes the ratios converge. This is a standard mathematical strategy, and in many contexts it works beautifully, but in eternal inflation the limit can fail to exist, or it can depend on the details of the cutoff procedure. A small change in how you regulate the infinity can shift the predicted distribution of observable quantities, so the theory can become less like a calculator and more like a menu of answers, each tied to a different measure choice. Often they do not converge, or they depend on how the cutoff was chosen. Different reasonable measures can predict different typical observers. Some measures reward volume so strongly that they favour regions that inflate longer, even if those regions are rare. Others try to avoid such youngness biases, where most observers would be predicted to live in extremely young universes. Still others attempt to track a single world line and count events along it, which can reduce some infinities but introduce other ambiguities. The difficulty is not that no measure can be written down, but that no measure is universally accepted as uniquely correct. This is not a minor technicality. It threatens the claim that eternal inflation is a predictive framework rather than a story generator. A predictive theory should tell us what to expect before we look, and it should risk being wrong. If the multiverse can be tuned by measure choices to match almost any observation, it becomes hard to falsify. That does not prove it is false, but it changes its scientific status in an uncomfortable way. The question becomes whether the measure can be derived from deeper principles, rather than chosen for convenience. The measure problem also connects to the arrow of time. If inflation is eternal, why do we find ourselves in a low entropy beginning rather than a generic high entropy fluctuation? The second law of thermodynamics tells us entropy tends to increase, so a low entropy past is a special condition. In ordinary cosmology, we accept that the early universe was smooth and low entropy. Then we ask why that was so. In an eternal setting, one might expect most observers to arise as fluctuations out of equilibrium, because equilibrium lasts forever. So why do we see a long, coherent history rather than a brief hallucination of order? This is not just philosophy. It is a consistency test for how probabilities are assigned. Some measures produce paradoxes like Boltzmann brains, observers arising from rare thermal fluctuations in empty de Sitter space. Avoiding them constrains the global picture. A Boltzmann brain is not a creature in a jar. It is a thought experiment about what dominates in an infinite future. If a universe approaches a de Sitter-like state with a tiny temperature, random fluctuations can, in principle, assemble complex structures given enough time. In an eternal space-time, enough time is guaranteed, and the rare can become common in absolute number. If most observers are predicted to be such fluctuations, then our ordered observations become atypical, which suggests the measure or the model is wrong. The multiverse must therefore thread a needle. It must allow our kind of history without making our kind of observer overwhelmingly unlikely. Even if the measure problem was solved, a second issue remains. If other bubbles exist, can any evidence of them reach us? Because inflation expands space so rapidly, most of the multiverse is causally disconnected from any given bubble interior. The horizon is not a wall, but it is a limit on what can influence us, and inflation tends to push potential influences away. Still, there are scenarios where bubbles form close enough that their future light cones intersect, leaving a chance for observable signatures. The question is not whether neighbours exist, but whether any interaction could leave a durable mark in our sky. The most discussed possibility is bubble collisions. If two bubbles nucleate near each other, their walls can expand and eventually intersect. The collision is not like two soap bubbles popping gently. It is a relativistic encounter between domain walls separating different vacuum states. The energy in the walls and the geometry of the collision can generate shocks, field perturbations, and anisotropic stress. From our perspective inside one bubble, the collision would occur in the very early universe, before the plasma fully settles into uniformity. It would be a scar laid down on the reheating surface, later stretched across the sky by cosmic expansion. A collision would be a violent event in the early history of our bubble. It could perturb the inflaton and the reheating surface, leaving a pattern in the CMB. The reheating surface is, in effect, a time-slice marking when our region became hot and radiation-filled. If a collision distorts that slice, it changes the initial conditions for the photon-baryon fluid that later produces the CMB anisotropies. That distortion can translate into a localized temperature modulation, a shift in the gravitational potential, and a specific polarization response. The signature is subtle, but it is conceptually clean. A coherent, non-random feature imposed on an otherwise statistically isotropic sky. The simplest predicted imprint is a circular feature on the sky. It could appear as a disk-like temperature anomaly with a specific radial profile. The circle arises because the intersection of our pass-like cone with a roughly planar disturbance on the reheating surface projects as a ring. Depending on parameters, the disk might be hotter or colder than average, with a gradual fall-off or a sharper edge. In maps, it would not look like the usual speckled noise. It would look like a deliberate mark, as if someone pressed a faint thumbprint onto the microwave sky. But the universe is messy, and chance patterns can also appear suggestive when we stare long enough. Polarization could carry a sharper signature. A collision can induce correlated E-mode patterns and potentially distinctive B-mode structure, depending on the dynamics. Polarization is generated when CMB photons scatter off electrons in a quadrupole radiation field, which makes it sensitive to coherent anisotropies. E-modes are the curl-free component, already detected with high precision, and they track density perturbations and velocity flows. B-modes are the curl component, harder to produce, and they can arise from gravitational waves or from lensing of E-modes by large-scale structure. A collision could, in some models, create a localized polarization pattern aligned with the temperature disk, adding a second channel of evidence. If temperature is the first clue, polarization is the cross-examination. The signal would not look like random Gaussian fluctuations. It would have symmetry and coherence that standard inflationary perturbations rarely produce. Gaussian fluctuations are statistically homogeneous and isotropic, meaning no special direction and no special place. A collision, by contrast, would pick out a direction, the axis pointing toward the impact region. It would also introduce phase correlations between modes, which is precisely what Gaussianity lacks. That makes the search conceptually straightforward. Look for anomalies that are too organized to be chance. Yet, too organized is a dangerous phrase, because humans are pattern-finding machines. But the searches are inconclusive. Some candidate anomalies have been reported, yet none has survived as a robust, unique collision signature. Analyses of WMAP and Planck data have looked for circular temperature features, Bayesian evidence for templates, and correlated polarization structures. A few cold spots and hemispherical asymmetries have attracted attention, but they can often be explained by ordinary statistics, foreground residuals, or a posteriori selection. A convincing detection would need multiple lines of support, a consistent temperature profile, a matching polarization pattern, and a significance that survives conservative trials factors. So far, the sky has not given us that clean convergence. There are practical reasons for that ambiguity. Foregrounds, noise, and the look elsewhere effect can create patterns that mimic rare signals. Our galaxy emits microwaves through dust, synchrotron radiation, and free emission, and removing those foregrounds is an art as well as a science. Instrument noise is not perfectly uniform, and scanning strategies can imprint subtle systematics that masquerade as cosmological features. Then there is the look elsewhere effect. If you search for enough patterns, some will appear significant by chance alone. To claim discovery, you must define the search in advance, or correct carefully for the freedom you gave yourself. In multiverse searches, that statistical discipline is especially important because the expected signals are not uniquely specified. There are also theoretical reasons. The collision imprint depends on unknown parameters like bubble wall tension, nucleation rate, and the internal inflation history. Wall tension affects how much energy is stored in the boundary, which influences how violent the collision is and how the disturbance propagates. The nucleation rate controls how often bubbles form and how close neighbours are likely to be. The internal inflation history matters because additional inflation inside our bubble can stretch and dilute the collision's effects. Even the shape of the inflaton potential after nucleation can change the mapping between a collision event and a CMB template. So the theory can predict a family of possible imprints rather than a single unmistakable pattern. If our bubble underwent enough additional inflation after nucleation, any collision scars could be stretched beyond our horizon. The same mechanism that hides prehistory can hide neighbours. Inflation is a cosmic eraser, and it does not discriminate between unwanted relics and potentially informative scars. A collision might have happened, and its disturbance might still exist, but it could have been inflated to scales larger than the observable universe. In that case, the imprint would be so smooth across our sky that it would look like a slight shift in background parameters, not a localized disk. This is one of the chapter's recurring ironies. The very process that makes the universe simple also makes its deeper context hard to detect. So the multiverse can be compatible with silence. That compatibility is both a strength and a weakness, because it makes non-detection hard to interpret. If we see no collisions, the multiverse is not ruled out, because collisions might be rare or hidden. If we do see an anomaly, it might still be a statistical fluke, or an astrophysical contaminant, or a systematic artifact. A good theory should be squeezed by data, but eternal inflation can sometimes slip through the squeeze by adjusting global assumptions. That does not make it wrong, but it raises the bar for what counts as persuasive evidence. Another possible window is spatial curvature. Bubble universes often begin with open geometry, which later inflation inside the bubble can dilute. In many tunneling scenarios, the interior of a nucleated bubble resembles an open Friedman, Lemaitre, Robertson, Walker universe with negative curvature. If inflation continues for many e-folds after nucleation, that curvature is driven towards zero, making the universe appear flat. But if inflation inside our bubble lasted only barely long enough, a small residual curvature could remain, detectable in principle through precise measurements of distances and the CMB. Curvature is therefore a potential fossil of how much inflation occurred after our bubble's birth. If inflation inside our bubble lasted only barely long enough, we might detect residual negative curvature today. Current constraints show the universe is extremely close to flat. Measurements combine CMB anisotropies, baryon acoustic oscillations, and supernova distances to infer the spatial geometry. So far, the best fit curvature is consistent with zero within tight error bars, which implies that if we live in a bubble with open geometry, internal inflation was generous. This pushes many bubble scenarios toward more internal inflation, and that has consequences for other signatures. The more inflation we had after nucleation, the less likely it is that we can see collision scars or curvature remnants. That near flatness pushes many bubble scenarios toward more internal inflation. More internal inflation makes curvature undetectable, and makes collisions less likely to be visible. It also makes our observable patch a smaller fraction of the bubble's total volume, which deepens the sense that our horizon is a narrow window. The universe can be vast and still look deceptively simple, because inflation smooths and flattens whatever it touches. So when we measure flatness, we're not just measuring geometry, we're indirectly measuring how much of our prehistory has been erased. That is a remarkable trade. The same observation that supports inflation also hides its most dramatic implications. Tensor modes provide another constraint. High-scale inflation often predicts primordial gravitational waves that would imprint B-mode polarization in the CMB. These gravitational waves are ripples in spacetime itself, generated by quantum fluctuations of the metric during inflation. Their amplitude is tied to the energy scale of inflation, often summarized by the tensor-to-scalar ratio, R. A detection of primordial B-modes would be a direct window into inflation's energy scale, and it would strongly shape which models remain viable. But B-modes are difficult because lensing by intervening structure converts some E-modes into B-modes, creating a foreground of its own. Non-detection of primordial B-modes already limits the energy scale of inflation and narrows the space of simple models. Eternal inflation can occur at many scales, but the constraints still bite. If inflation happened at a lower energy scale, primordial gravitational waves would be weaker, and B-modes would be harder to detect. Some eternal inflation scenarios live comfortably at low scales, while others prefer high plateaus that are increasingly constrained. The point is not that non-detection kills inflation, but that it trims the garden of possibilities. In a field where models can proliferate, trimming matters. Non-Gaussianity is another filter. Many complicated inflationary dynamics produce measurable non-Gaussianity, yet observations strongly favour near-Gaussian initial conditions. Non-Gaussianity shows up in higher-order correlations like the bispectrum, and it can indicate interactions among fields during inflation. Single-field slow-roll inflation tends to produce very small non-Gaussianity, while multi-field models, sharp features, or non-standard kinetic terms can enhance it. So the observed near-Gaussianity is both a clue and a constraint, pointing toward a remarkably simple mechanism, or toward dynamics that hide their complexity. In the multiverse context, it also limits how wild the local inflationary physics inside our bubble could have been. That simplicity is a clue and a constraint. It suggests the mechanism generating perturbations was remarkably clean, or that messy alternatives are suppressed. Clean does not mean trivial, it means the early universe behaved in a way that left a mathematically simple statistical imprint. The CMB's pattern is not random in the everyday sense. It is random with a particular structure, and that structure is diagnostic. When we say close to Gaussian, we are saying the universe's earliest accessible fluctuations behave like a well-characterized quantum process. So every new limit on non-Gaussianity is a statement about what the inflaton could and could not have been doing. So the testable footprint of eternal inflation is indirect. It must be consistent with tight limits on curvature, tensors, and non-Gaussianity, while still allowing global self-reproduction. This is a delicate balancing act, because the global behavior depends on the inflaton potential at high field values, while our observations constrain the potential where our modes were generated. The same potential must do two jobs: produce the right perturbations locally and allow quantum kicks to dominate somewhere else. In some models, that is natural. In others, it requires careful tuning. The multiverse, in other words, is not automatically implied by inflation, even if it can arise from inflation under certain conditions. This is where the narrative tension sharpens. Eternal inflation offers an answer to before by dissolving the idea of a single beginning, but it risks moving the origin question into a domain that may be fundamentally unobservable. The global structure could be real and still leave us no decisive evidence, and if decisive evidence is forever out of reach, we have to ask what kind of claim we are making. Is it a scientific inference, constrained by data, or a metaphysical picture that rides alongside the equations? The boundary between those categories is not fixed. It shifts with new observations and new theoretical insights. The multiverse is often invoked for another reason. It offers a possible explanation for the cosmological constant. The small but non-zero value of LL is not just a number in an equation. It controls the late-time acceleration of the universe and sets a vacuum energy scale that is puzzlingly tiny. When we measure the expansion history with supernovae, the CMB, and large-scale structure, we find that the universe's expansion is speeding up. In Einstein's equations, that acceleration can be described by a cosmological constant or by something that behaves like it. Either way, the effective energy density associated with L is extraordinarily small compared with particle physics scales. Quantum field theory naively predicts enormous vacuum energy. Observations demand a value many orders of magnitude smaller, yet not exactly zero. In quantum field theory, each mode of a field contributes a zero-point energy, and summing those contributions up to high energies yields a huge value. Renormalization teaches us that only differences in energy are physically meaningful in many contexts, but gravity couples to absolute energy density. So the cosmological constant problem is not merely a calculation error. It is a clash between how quantum fields count vacuum energy and how space-time responds to it. The observed L is small enough to be baffling, but large enough to dominate the universe's fate. That combination is what makes it feel like a message we have not learned to read. In a multiverse, different bubbles could realize different effective vacuum energies. Observers would only arise in bubbles where L allows galaxies to form. If L were too large and positive, accelerated expansion would prevent matter from clumping into stars. If L were too negative, the universe could recollapse too quickly. This argument is often framed in terms of structure formation. Galaxies require time and gravitational instability to amplify small density perturbations. A large positive L shuts off that growth by pulling space apart faster than gravity can gather matter. A large negative L can end the story early, collapsing the universe before heavy elements and long-lived stars can appear. so the observed smallness of L can be seen as living near a boundary where galaxies are still possible. This is anthropic reasoning, and it is controversial. It does not derive L from first principles, it conditions on the existence of observers. Supporters argue it turns a fine-tuning mystery into a selection effect. Critics argue it weakens explanation by replacing dynamics with environmental happenstance. The controversy is not about whether selection effects exist. It is about whether they are the best available scientific account or a sign of missing physics. If anthropic reasoning is used too freely, it can become an excuse to stop searching for deeper mechanisms. If it is rejected too rigidly, it can ignore a real statistical fact. We can only observe conditions compatible with our existence. Anthropic arguments also depend on the measure problem. To say we are likely to observe a certain L, we must define probabilities across bubbles. If the multiverse produces infinitely many bubbles with different L values, then likely is not a simple word. It depends on how we weight bubbles, how we count observers, and how we regulate the infinities. A measure that favors volume might heavily weight bubbles that inflate longer, even if their L values are atypical. A measure that favors certain time slicings might bias toward younger regions, changing the predicted distribution again. So the anthropic explanation for L is only as solid as the probability framework behind it. So the cosmological constant problem and the measure problem become entangled. The multiverse can explain L only if it can also define what typical means. This is where the multiverse shifts from a poetic idea to a technical program, because it demands a consistent statistical mechanics of spacetime. If that program succeeds, it could transform a fine-tuning puzzle into a probabilistic prediction. If it fails, the multiverse remains suggestive but scientifically slippery. And that uncertainty is part of the chapter's mood. We're walking along the edge of what can be computed and what can be asserted. At this point, another framework enters the story. String theory suggests a vast landscape of possible vacuum states, each with different low-energy physics. In string theory, the fundamental objects are not point particles but extended entities, and consistency often requires extra spatial dimensions. Those extra dimensions cannot be large and obvious, so they are typically compactified, curled up into shapes too small to see directly. The shape and topology of that compact space, along with background fluxes threading through it, determine the effective physics in the large dimensions. So what looks like the laws of nature may depend on hidden geometric choices. In string theory, extra dimensions must be compactified in specific shapes and flux configurations. Different compactifications can produce different particle spectra and coupling constants. One vacuum might yield different masses, different symmetry breakings, or different strengths of forces. Some vacua may be unstable, decaying quickly, while others can be metastable and long-lived. The number of possible configurations can be enormous, which is why the term landscape is used. It is a conceptual terrain of valleys and plateaus, each valley representing a vacuum with its own low-energy parameters. In that terrain, our observed universe would correspond to one particular valley among many. This is the string landscape, a menu of metastable vacua. Each vacuum corresponds to a different effective set of laws at low energies. The landscape idea did not arise as a philosophical desire for many universes. It emerged from the mathematics of compactification and flux choices. Still, its implications are hard to ignore, because it suggests that uniqueness may not be guaranteed by consistency alone. If there are many consistent vacua, then the question why these constants becomes sharper, not softer. It becomes a question of selection, dynamics, or statistics across the landscape. Eternal inflation provides a mechanism to populate that menu. Quantum tunneling and vacuum decay could move regions from one vacuum to another, producing bubbles with different constants. In this combined picture, the inflating background is like a generator that explores the landscape over time, sampling different vacua through rare transitions. A region in one vacuum can tunnel to another, nucleating a bubble whose interior inherits the new vacuum's low-energy physics. Some transitions might be more probable than others, depending on barrier heights and vacuum energies. The result is a cosmic patchwork, different bubbles, different constants, and different histories, yet all arising from the same underlying framework. In that combined picture, our observed laws are not uniquely selected by consistency alone. They are one realized option among many, stabilized in our bubble. This is a powerful synthesis, but it inherits the same skepticism. A large landscape can make almost any outcome possible, which can dilute predictive power. It also raises a deeper question about what counts as an explanation. If the laws vary across bubbles, then why these laws becomes why this bubble. And if the answer is, because otherwise we would not be here, we have to decide whether that is satisfying science or an admission of limits. The central question returns in a new form. Did anything exist before the Big Bang, or is the Big Bang just our local entrance into a larger structure? Eternal inflation suggests a kind of prehistory without a first moment. The inflating background can extend indefinitely, at least to the future, and perhaps to the past in some models. But past eternity is not guaranteed. Some theorems suggest inflating spacetimes are past incomplete under broad conditions, meaning inflation may still require a beginning. That phrase, past incomplete, means that if you follow certain trajectories backward in time, you reach a boundary in finite proper time. It does not tell us what lies beyond the boundary, but it warns us that inflation may not remove the need for an origin. So even eternal inflation may not be eternal in both directions. It can replace one beginning with another boundary, possibly in a quantum gravity regime. That boundary might be a true beginning, or it might be a transition from a different phase where classical spacetime is not the right language. Either way, it keeps the series stakes high. The multiverse does not automatically solve the origin problem. It changes its location and its language. Instead of asking what happened at t=0, we ask what defines the domain where t is meaningful. And that is a harder question, because it asks for the foundations of time itself. We end this chapter with a practical pivot. If the multiverse is real, the best tests may be constraints rather than direct sightings. Constraints come from the sky's geometry and statistics. Every non-detection of curvature, tensors, and non-Gaussianity trims the space of inflationary histories. More precise CMB polarization maps can tighten tensor limits and search for subtle anisotropies. They can also test for specific collision templates and unusual mode couplings. In the visuals, this is where the narrative becomes forensic. The universe is a crime scene, and the CMB is the photograph taken long after the event. We are looking for fingerprints that may have been smudged by expansion, yet not completely erased. Large-scale structure surveys add leverage by measuring many more modes than the CMB at some scales. Galaxies trace the underlying distribution of matter, and their clustering encodes the same primordial perturbations in a different medium. By mapping millions of galaxies, surveys can test for features in the power spectrum, scale-dependent biases, and departures from statistical isotropy. They can also cross-correlate with CMB lensing, which measures how intervening matter deflects CMB photons. Each dataset is imperfect, but together they form a network of consistency checks. If eternal inflation leaves any subtle imprint, it may appear as a tension between datasets, or as a pattern that repeats across independent probes. Even so, definitive proof may remain elusive. A multiverse can be compatible with our data while hiding its global structure beyond our horizon. That is the cost of dissolving the beginning. The answer to before becomes elsewhere, and elsewhere may be permanently out of reach. This is the chapter's lingering unease. A theory can be true and still be inaccessible, and cosmology has to decide how to live with that. We can demand testability, but we cannot demand that nature arrange itself for our convenience. So we are left with a tension between ambition and humility, between wanting a complete story and accepting observational limits. Yet the idea also points toward an even stranger possibility. If many bubbles exist, perhaps spacetime itself is not fundamental, and bubble boundaries are emergent descriptions. This is not a new topic so much as a pressure that builds inside the old one. When we talk about bubbles, boundaries, and vacua, we are already treating spacetime as something that can change, phase, decay, and reorganize. That language hints that spacetime might behave like a material, with properties that arise from deeper degrees of freedom. If that is true, then the multiverse is not just many regions in space. It is a clue about what space is. If spacetime is emergent, then before might not be earlier in time at all. It might be a deeper layer of description where time is not yet defined. In that layer, the question, what happened before, becomes, what conditions give rise to time? That is a profound shift, because it replaces chronology with structure. Instead of a timeline, we imagine a hierarchy of descriptions, where our familiar spacetime is a large-scale approximation. The multiverse, in this view, is not merely a proliferation of beginnings, it is a symptom that our notion of beginning is incomplete. The next chapter follows that haunting lead. We ask whether the beginning is not a moment, but a phase change in what reality is made of, at the threshold where time and space may dissolve, before the Big Bang becomes less a place in history and more a test of what reality is made of, an invitation to replace certainty with better questions, and to let evidence, not intuition, decide what the beginning truly means. Before the first atom, before the first light, before space had a single direction to point in, what was the universe actually like? And can before even mean anything at all? Chapter 6 turns the question inside out, because looked like assumes space-time is already the stage, already laid out with distances, durations, and a place for events to happen. If space-time is not fundamental, then the beginning is not a moment in time, and it is not an explosion inside a pre-existing arena. It is a change in description, where familiar geometry becomes a derived, late-arriving approximation, useful, predictive, and real in practice, yet not the deepest language. Chapter 3 warned that the singularity is a breakdown of classical general relativity, not a photographed event, and that the equations are telling us where their own authority ends. Chapter 4 tested bounces that keep time continuous, and found costs in stability and initial conditions, because contraction tends to amplify anisotropy, and shear unless something very special suppresses them. Chapter 5 multiplied beginnings with eternal inflation, and exposed the measure problem and observational limits where anything happens somewhere becomes hard to convert into a clean prediction. Now we follow the pressure building underneath all of them, models where spacetime itself is emergent, and where the word origin points to a deeper layer than curvature. We set a rule again. Any origin story must say what replaces spacetime, not just what precedes it. That replacement must still reproduce the evidence we trust, including the CMB and light element abundances, because those are not philosophical preferences but measured fossils. It must also confront the arrow of time, because low entropy is not optional background scenery, and because gravitational clumping makes special initial conditions unusually expensive. And it must be honest about its hidden assumptions, because every escape needs a deeper rulebook, one that can be questioned, compared, and ideally tested. Start with the oldest temptation in high-energy theory, extra dimensions. The idea is older than string theory, reaching back to Kaluza and Klein, who noticed that adding a tiny extra direction could unify gravity with electromagnetism in a single geometric framework. In modern proposals, the universe has more spatial directions than the three we experience, and those directions can be compact and tiny, or large but hidden by how fields are confined. The key move is that our visible universe can be a brane, a three-dimensional membrane in higher space, embedded like a sheet inside a larger volume. Matter and light might be trapped on the brane, while gravity can leak into the bulk, because the graviton is tied to geometry itself rather than to a particular gauge field. That leakage is not just a metaphor because it changes how gravity behaves at short distances, and it can alter the relationship between energy density and expansion. In some brane world setups, the Friedmann equation gains extra terms, including quadratic energy density corrections, which matter most at the highest temperatures. So the early universe becomes a place where the same energy can bend spacetime differently, depending on how the brane sits in the bulk. Visually, this is a shift from a self-contained stage to a layered architecture. We can imagine a dark, higher dimensional expanse, quiet, almost featureless, while a luminous membrane carries the familiar drama of particles, radiation, and chemistry. On that membrane, photons race along paths that never leave the surface, while gravitational influence can bow outward, spreading into dimensions we do not directly traverse. Even the notion of distance becomes two-tiered, what we measure with rulers on the brane, and what exists as separation in the bulk. Brane cosmology offers a new way to picture a beginning without a singular point. The hot Big Bang can be reinterpreted as a brane event, like a collision or close approach, where the energy of motion in the bulk is converted into heat on the brane. In ekpyrotic-inspired versions, two branes drift in a higher dimensional bulk and then interact, guided by an effective potential that controls their approach. To a brane-bound observer, that interaction looks like a sudden heating into a dense plasma, as if the universe ignites everywhere at once. The before is not earlier in our four-dimensional time alone, but motion in the extra dimension, which is why the word before becomes slippery rather than simply forbidden. From our perspective, time may appear to begin at the heating event, while in the bulk there can be a longer story of trajectories, separations, and forces. This is a conceptual trade. The singularity is avoided, but the bulk becomes the new arena whose own origin is not automatically explained. So the brain picture does not erase the question, it relocates it, like moving a boundary to a deeper layer. This is dramatic, but it is also constrained by the same forensic rules. A brain collision must still yield a radiation-dominated universe quickly enough for BBN to work, because the neutron-to-proton ratio freezes out on a strict timetable. It must also generate the observed nearly scale-invariant, nearly Gaussian perturbations, which are mapped in exquisite detail across the CMB sky. Those perturbations are not decorative, because they seed galaxies and clusters, and they encode the physics of whatever set the initial conditions. Ekpyrotic mechanisms can smooth contraction with an ultra-stiff component, suppressing anisotropy growth, because a component with equation of state parameter W much greater than 1 dilutes shear faster than it dilutes itself. That is the technical heart of the ekpyrotic appeal. Contraction usually becomes chaotic, yet an ultra-stiff field can act like a cosmic stabilizer, but they often need multi-field dynamics to get the right curvature spectrum without large isocurvature, because a single ekpyrotic field tends to generate the wrong kind of perturbations. Observations strongly limit isocurvature, so conversion must be efficient and controlled. Otherwise, the model leaves fingerprints the sky has not shown us. There is also a subtlety about what collision means in a quantum theory. At the highest energies, the brains are not rigid objects like sheets of metal, and their interaction is mediated by fields, tensions, and quantum fluctuations. The heating event must be described as a transition in degrees of freedom, where kinetic energy in the bulk becomes particle excitations on the brain. That translation is where many models live or die, because it must be both mathematically consistent and observationally quiet. Extra dimensions also raise a sharper question about what counts as space. If our space is a brain, then geometry is partly a property of embedding, not only intrinsic curvature, and the distinction matters when you ask what can exist outside our familiar directions. That suggests a new kind of prehistory, where the bulk exists even if our brain time is ill-defined, and where our apparent beginning is a local event in a larger structure. Yet the bulk is not automatically observable, because confinement can hide it almost perfectly, leaving us with gravity as the only messenger. So the scientific question becomes whether extra dimensions leave any durable imprint in our sky. One place to look is in deviations from Newton's inverse square law at sub-millimeter scales, where extra dimensions could change how gravitational flux spreads. Laboratory tests already push hard on this, using torsion balances and precision measurements that search for tiny departures from standard gravity. Another place to look is the early universe, where high-energy densities might excite Kaluza, Klein modes, massive echoes of fields moving in compact directions. Possible signatures exist, but they are narrow and model-dependent. Kaluza, Klein modes can modify gravity at small scales, though laboratory tests already constrain them, and astrophysical systems add further limits through orbital dynamics. In the early universe, extra-dimensional dynamics can alter the tensor spectrum and its tilt, changing how primordial gravitational waves distribute power across frequency. Some brain scenarios predict distinctive gravitational wave shapes, sometimes blue-tilted at high frequencies, which would be faint in the CMB yet stronger in interferometers. Future detectors could test that, if astrophysical backgrounds can be separated cleanly, because compact binaries produce a confusion signal that can mimic or hide primordial relics. The key is not merely detection, but identification, spectral slope, polarization content, and consistency with nucleosynthesis bounds on extra radiation. But the same flexibility that makes brain models adaptable can make them hard to falsify, because adjustable potentials and couplings can be tuned to imitate more conventional predictions. That's a warning sign, not a verdict, and it tells us to demand sharper, less negotiable outputs. So we set a rule again. A higher dimensional story must not become a menu of adjustable outcomes. If the model can fit any spectrum by tuning hidden geometry, it stops being an explanation, and it becomes a catalogue of possibilities. The brain picture can move the singularity problem, but it can also move the arbitrariness, pushing it into the shape of the bulk and the placement of the brain. We have not yet escaped the question of why these dimensions, and why these boundary conditions, and why the universe chose this particular embedding. From extra dimensions, we pivot to a different kind of depth, holography. The holographic principle begins with a counterintuitive claim about information and gravity, and it is rooted in a concrete calculation rather than a metaphor. The maximum information in a region scales like the area of its boundary, not its volume, which runs against the everyday idea that more space means more capacity. Black hole thermodynamics motivates this, because entropy tracks horizon area in Planck units, and because the Bekenstein-Hawking formula looks like a law of nature. Historically, this grew from a crisis. If you throw matter into a black hole, the entropy seems to disappear behind the horizon, yet the second law demands that total entropy should not decrease. The resolution was radical. The black hole itself carries entropy proportional to area, as if the horizon is a physical ledger of microscopic states. That ledger hints that gravity counts information differently, and that spacetime might be an encoding, not a container. AD-CFT is the proof of concept that makes holography more than poetry. It relates a gravitational theory in a bulk spacetime to a quantum field theory on its boundary, and it does so with an exactness that allows calculations on one side to answer puzzles on the other. In that duality, bulk geometry emerges from boundary degrees of freedom and their entanglement structure, which is why entanglement becomes more than a quantum curiosity. The boundary theory has no gravity, yet it can encode black holes and bulk causal structure, including horizons and thermodynamic behavior. This is one of the clearest hints that spacetime can be emergent from non-spacetime physics. If a lower dimensional theory can reproduce a higher dimensional gravitational world, then dimension begins to look like an effective attribute rather than a fundamental label. Even the idea of distance can be reconstructed from patterns of correlation, as if geometry is the shadow cast by quantum relationships. That is an unsettling thought, because it suggests that the universe's most basic stage directions may be derivative. But our universe is not asymptotically anti-de Sitter, at least not on large scales. Observations suggest late-time acceleration consistent with an approximately de Sitter geometry, with a small positive cosmological constant, or something that behaves similarly. A clean de Sitter holography is not settled, so applying the lesson to cosmology is difficult, and the technical obstacles are not cosmetic. De Sitter space has horizons, finite entropy, and a different notion of boundary, so the usual ADS toolkit does not transfer smoothly. Still, the conceptual shift matters, because it reframes the beginning as a boundary condition in a dual theory, rather than as a violent event inside spacetime. In that framing, before the Big Bang might be the wrong coordinate question, like asking what is north of the North Pole. The deeper question becomes what state the boundary theory was in, and how geometry emerged from it, and whether that emergence is generic or finely selected. If the boundary description is fundamental, then the universe's earliest moment could be a particular quantum state, rather than a point in time. Holography also forces the information question into the center of cosmology. If the fundamental description is quantum and unitary, then information should not be destroyed, even when geometry becomes extreme and classical intuition fails. That echoes the black hole information problem, where evaporation seems to erase details, and where semi-classical reasoning collides with quantum principles. Many holographic arguments insist unitarity survives, and geometry must adjust to preserve it, which is a profound constraint on what spacetime is allowed to do. If so, a cosmological beginning might also be constrained by unitarity, not only by curvature. A beginning that discards information would be less like a physical process and more like a reset button, and quantum theory resists that kind of erasure. Yet unitarity is not a free win, because it collides with our intuition about beginnings, and it sharpens the discomfort we already feel. A universe that starts in a special low entropy state looks like information was selected, and selection demands an explanation. If evolution is unitary, then that selection must be encoded in the initial quantum state. So the question becomes what principle picks that state, and why it is so extraordinarily simple, given how many complicated states are possible in the same Hilbert space. This is the arrow of time problem returning now in quantum clothing, and it refuses to be dismissed as mere philosophy. Entropy is not just disorder, it is a count of possibilities, and low entropy is a statement about improbability. Now we pivot from holography to the broader idea it suggests: emergent spacetime. Emergent does not mean unreal, it means collective and approximate, like a pattern that becomes stable when many components act together. Temperature is emergent from atoms, even though temperature can be measured precisely, and even though it governs engines, storms, and the habitability of planets, fluid pressure is emergent from molecular collisions, even though pressure shapes weather and oceans, and even though it can crush steel at depth. In the same way, spacetime could be emergent from more fundamental quantum degrees of freedom. The metric might be like a thermodynamic variable, summarizing a deeper microphysics that we do not directly observe, and that only becomes visible through its collective effects. When we say space expands, we may be describing a coarse-grained behavior, not the fundamental motion of a pre-existing fabric. The question then becomes what the microscopic constituents are, and what conditions make geometry the right effective language. One leading intuition is that geometry is built from entanglement. In holographic examples, changing entanglement changes the connectivity of the emergent bulk, and that relationship can be made quantitative through tools like entanglement entropy. Less entanglement can correspond to pinched geometry, or even disconnected regions, as if the spacetime manifold tears along seams of weak correlation. More entanglement can correspond to smooth, connected spacetime with well-defined distances, where causal structure behaves in the familiar way. In this view, the metric is not a primitive field, but a bookkeeping device for correlations translating how strongly systems talk to each other into how far apart they are. That is why emergence is not merely aesthetic, it is operational. It tells you what measurements mean when geometry is not assumed. If correlations define distance, then the earliest universe might be describable as a network of relationships before it becomes describable as a manifold. The Big Bang would then mark a phase where the network acquires a geometric interpretation. This changes what nothing could mean. If spacetime is emergent, then nothing is not empty space with no particles, because empty space already presumes geometry and a vacuum state defined on that geometry. It could be a state with no geometric interpretation, where the variables are not spatial at all, and where here and there are not yet meaningful categories. The universe would not arise by filling a pre-existing void, but by entering a phase with geometry, like a material condensing into a crystal with a new order. The Big Bang would be like condensation, where a new effective language becomes valid. We can picture an abstract quantum substrate, featureless to our eyes, suddenly developing stable patterns that behave like distances, clocks, and causal cones. In a laboratory, phase transitions leave telltale defects and correlations, and cosmology asks whether an analogous transition could leave imprints in primordial spectra. But emergence does not automatically solve the beginning. It relocates it, and relocation is not resolution. We still must specify the underlying degrees of freedom and their dynamics, because emergent is a label, not a mechanism. We still must explain why the emergent phase looks like a hot, nearly homogeneous universe, rather than a patchwork of incompatible regions. We still must explain why the initial perturbations are nearly Gaussian and adiabatic, because the data show a striking simplicity that is hard to fake. And we still must explain why the early state has such low gravitational entropy, meaning why the geometry began so smooth when gravity prefers clumping. At this point, time itself becomes the next target. If space can be emergent, then time might also be emergent, or at least not fundamental, and that possibility is not a poetic flourish. In quantum gravity, time is often not an external parameter, but a relational variable, because the Wheeler-DeWitt framework treats the universe's quantum state as timeless in a particular technical sense. Clocks are physical systems, and their readings depend on correlations within the universe, which means time is something the universe does, not something it sits inside. So, before may fail, not because we lack data, but because the concept is not basic. If the most fundamental description has no time parameter, then earlier and later emerge only in regimes where certain degrees of freedom behave like reliable clocks. That is a hard idea to visualize, so we lean on analogy. In thermodynamics, temperature makes sense only when many particles allow a stable average. Likewise, time might make sense only when the universe is in a phase where correlations permit a consistent ordering of change. This is where no boundary ideas enter the story. The Hartle. Hawking proposal replaces a sharp beginning with a smooth geometry in imaginary time, using a mathematical trick where time is rotated into a spatial-like direction to tame singular behavior. Near the origin, time behaves like a spatial direction, removing a boundary like the North Pole, where the surface ends smoothly without an edge. There is no first instant in the classical sense, because the geometry rounds off smoothly, and the path integral weights compact, regular histories. The universe can then transition to real time, where expansion and causal structure emerge, and where the familiar notion of a forward arrow can be discussed again. Visually, the story is not a bang, but a rounding, like a smooth cap on a cone that would otherwise end in a point. The early geometry is Euclidean in character, then it becomes Lorentzian, and the change is less like a jump and more like a change of regime. But the elegance of the picture hides a difficulty. We must still interpret what the wave function means and what it predicts. This is not a settled picture, because interpretation is contested. Some treat it as a literal claim about the universe's quantum state, suggesting that the no-boundary condition is a physical selection principle. Others treat it as a calculational prescription for weighting histories in a path integral, a tool that produces amplitudes without necessarily describing a single realized geometry. There are debates about what probabilities mean and what counts as a prediction, especially when there is only one universe and no external ensemble. Yet the core narrative beat is clear. Replace a singular start with a rounded quantum geometry. The proposal tries to make the beginning less like an exception and more like a regular solution, where the same rules apply everywhere on the manifold. But even here, the rules are doing the heavy lifting, and we must ask why those rules, and why that choice of boundary condition. The no-boundary idea is a candidate grammar for beginnings, not the final word. A close cousin is quantum tunneling from nothing, often associated with Vilenkin-style proposals. Here the universe nucleates as a quantum event, like tunneling through a barrier, and the language is borrowed from quantum mechanics, where classically forbidden transitions occur with calculable probability. The nothing is not philosophical non-being, it is a specific quantum state with a framework, often described as the absence of classical space-time rather than the absence of law. It still assumes laws, a configuration space, and a rule for amplitudes, which means the model begins with structure even as it claims to begin from nothing. So the model does not answer why there are laws, it uses laws to describe a beginning. That is not a fatal flaw, but it is a boundary on what the model can claim, and it is where language can mislead the audience. When we hear nothing, we imagine emptiness, yet the calculation assumes a quantum gravitational setting with allowed histories and a notion of probability. The real claim is narrower. Given a certain framework, a universe-like state can nucleate without a prior classical time. This caveat is the chapter's central tension. Every attempt to avoid the singularity invokes a deeper structure that is not explained within the model, and the deeper structure becomes the new place where why accumulates. Extra dimensions assume a higher dimensional arena with its own dynamics and stability, including mechanisms that keep extra directions compact and prevent catastrophic instabilities. Holography assumes a boundary theory, and a correspondence that is itself a law-like statement, and correspondences are not self-justifying. No boundary and tunneling assume a path integral or a wave function of the universe, and those assume a measure, an inner product, and a prescription for extracting predictions. Each route changes the question from what happened to what is the correct framework, and that is both progress and provocation. Progress, because it clarifies what must be specified, and provocation, because it exposes how much is being assumed. The singularity was a warning sign, and the warning does not vanish when we rename the problem. Now we confront the word that keeps misleading us: vacuum. In quantum field theory, empty space is active, because fields have zero-point fluctuations, and because the lowest energy state still carries irreducible quantum uncertainty. Virtual excitations appear in calculations, and vacuum energy contributes to stress energy, which is why the vacuum can gravitate in principle. This is why nothing in physics is rarely nothing in ordinary language, and why popular accounts can accidentally smuggle in assumptions. Yet vacuum activity does not automatically create universes without extra assumptions. Fluctuations in a vacuum are constrained by conservation laws and by the background space-time, because vacuum is defined relative to a particular geometry and a particular notion of time translation. In flat space-time, the vacuum is stable under ordinary conditions, and fluctuations do not accumulate into macroscopic objects without an energy source. In curved space-time, changing geometry can produce particles, but the process depends on dynamics, such as expansion rate and horizon structure. To get a whole universe, one needs a gravitational setting and a rule for initial conditions, so vacuum fluctuations are ingredients, not a complete origin story, and they do not by themselves answer why there is a stage on which fields fluctuate. Even inflation, which amplifies quantum fluctuations into classical density variations, presupposes a background spacetime and a field in a special state. So when someone says, the universe came from a vacuum fluctuation, the scientific response is to ask, which vacuum, defined where, and under what dynamics? Vacuum energy also connects to instability and the cosmological constant problem. If naive zero-point energy gravitated directly, the universe would curve violently, because the predicted vacuum energy density from quantum fields is enormous compared to what we infer from cosmic acceleration. Instead, we observe a tiny effective L that dominates only at late times, and it is one of the sharpest mismatches between theory and observation in modern physics. Any quantum creation scenario must coexist with this puzzle, not ignore it, because the vacuum is part of the gravitational budget. If vacuum energy can be tuned or selected, we must ask what selects it. If it is environmental, we are back to multiverse logic and its measure ambiguities, where probabilities become hard to define and harder to test. If it is dynamical, we must specify the mechanism and show it does not spoil nuclear synthesis, structure formation, or the observed near flatness of the universe. Either way, vacuum becomes a doorway into deeper questions about what counts as a fundamental parameter. The information question returns again, now sharpened by beginnings. If the universe begins by tunneling, is evolution unitary across that event? Or does the nucleation define a new Hilbert space with no continuity to anything prior? If the universe begins by no boundary rounding, what is the Hilbert space and its inner product? And how do we interpret the wave function's weighting of different histories? If spacetime emerges from entanglement, what is the underlying unitary evolution parameter, and how does it relate to the emergent time we experience? These are technical questions, but they translate into a simple narrative demand. Does the beginning preserve information, or does it define what information even means, and can those options be distinguished by observation? In ordinary physics, unitarity is a bookkeeping rule that ensures probabilities add up, and that evolution is reversible at the microscopic level. In cosmology, unitarity becomes a statement about whether the universe has an internally consistent account of its own origin. Black holes are the conceptual cousin that keeps us honest. They taught us that horizons mix geometry, thermodynamics, and quantum theory in one problem, and that you cannot fix one piece without disturbing the others. They forced the idea that area counts information, and that unitarity may constrain spacetime, because Hawking radiation makes the question operational rather than metaphysical. Cosmology is now asking for the same synthesis, but without the comfort of an external observer who can stand outside and watch. A black hole has an outside region where we can define time and measure radiation, and that outside region anchors our calculations. The universe has no outside, so the bookkeeping must be internal and self-consistent, and even the meaning of probability must be handled with care. When the whole cosmos is the system, there is no larger clock to reference, and no external environment to average over. That is why cosmological quantum theory feels different, and why beginnings are so conceptually sharp. So we set a rule again. Any origin of nothing must define its notion of information. If it cannot say what is conserved, it cannot say what is explained, because explanation in physics is tied to invariants and symmetries. If it cannot define probabilities, it cannot connect to observation, because data analysis is a probabilistic enterprise even when the data are precise. If it cannot specify a state selection principle, it cannot address the arrow of time, because low entropy is a selection whether we like it or not. This is where mystery becomes methodology, because the rules are part of the claim. A model is not only a story about what happened, it is a prescription for what questions are meaningful and what quantities can be computed. When spacetime is emergent, the model must tell us how to recover locality, causality, and the approximate independence of distant regions. Those are not optional features, because our universe behaves locally to extraordinary precision. Now we ask the practical question, what could we actually test? Extra dimensions might leave signatures in primordial tensor spectra, and their frequency dependence, because the propagation of gravitational waves can feel the bulk in ways photons cannot. Brain dynamics could imprint features or non-Gaussianity patterns distinct from simple slow-roll inflation, especially if the heating event is abrupt or involves multiple fields. Holographic or emergent spacetime models might predict specific consistency relations among correlators, linking the 2-point and higher point functions in ways that standard scenarios do not. Some could modify the initial vacuum choice, leaving oscillations or cutoffs in the scalar spectrum, which would appear as subtle ripples in the angular power spectrum of the CMB. But the observational window is narrow, because the CMB and large-scale structure already constrain simplicity, and because many exotic models are forced to mimic the same near-scale invariant output. So the game becomes one of precision and pattern recognition, not of dramatic deviations. We are looking for small, stubborn anomalies that survive improved calibration and independent datasets. Primordial gravitational waves are the most direct probe of ultra-early dynamics. Different scenarios shift power between CMB scales and higher frequency bands, because the mechanism that produces tensors also sets their spectral tilt and amplitude. A blue tensor tilt could hide from B-mode searches yet appear in interferometer windows, which is why multiband gravitational wave cosmology is so promising. Future detectors can map a stochastic background across decades of frequency, turning a single number into a spectrum with shape and structure. The challenge is subtraction, because astrophysical binaries produce their own backgrounds, and because unresolved populations can masquerade as a smooth stochastic signal. So a primordial claim must be supported by spectral shape, cross-correlation, and consistency with BBN bounds, since too much gravitational wave energy density would change the expansion rate during nucleosynthesis. This is one of the chapter's recurring themes. Early universe freedom is constrained by later universe fossils. The universe is a closed book in some ways, yet it left marginal notes in the margins of multiple epochs. Primordial spectra also carry clues in their deviations from a pure power law. A cutoff at large scales could hint at a finite prehistory or a non-standard initial state. Though cosmic variance makes the larger scales the hardest to read with confidence, oscillations could hint at boundary conditions matching events or new physics near a transition, like interference fringes left by a sharp change in the underlying dynamics. Non-Gaussianity could reveal interactions that are invisible in the 2-point function, because higher point statistics are sensitive to couplings and field content. But cosmic variance limits the larger scales, and systematics complicate subtle features, which means we must be careful not to turn noise into narrative. Foregrounds from our galaxy, instrument beam effects, and analysis choices can all sculpt apparent anomalies, and the history of cosmology includes lessons about premature certainty. So the standard of evidence must be high, because the sky is noisy in exactly the places we most want to read. The mystery is real, but so is the temptation to overinterpret. There is also the possibility of relic defects tied to high-energy structure. Extra dimensions and brain dynamics can produce cosmic strings or string-like remnants, either as fundamental objects or as effective defects formed during symmetry breaking. Such defects would leave line-like discontinuities, lensing signatures, and gravitational wave bursts, and they would act as persistent artifacts of the early universe's microphysics. Current limits already constrain many defect networks, but not all parameter space is closed, especially for low-tension strings that are hard to detect. A detection would not prove a specific origin model, but it would confirm new high-energy structure, and it would narrow the space of plausible frameworks. It would also anchor speculation to a measurable object, which is the currency of cosmology, and it would turn abstract talk of brains and extra dimensions into a concrete signal. Even a non-detection is informative, because it trims models that rely on defect formation as a generic outcome. In cosmology, absence can be evidence, provided the search is sensitive and the prediction is robust. Yet the climax of this chapter is not a single model winning. It is the realization that every model replaces the singularity with a deeper assumption, and that the deeper assumption is where the true debate lives. The singularity was a sign that spacetime cannot be the final layer, because classical geometry cannot describe its own birth. Extra dimensions say spacetime is bigger than we thought, and that our observed universe may be a subspace with special confinement properties. Holography says spacetime is an encoding of information on a boundary, and that bulk gravity may be a translation of non-gravitational quantum dynamics. Emergence says spacetime is collective behavior of quantum degrees of freedom, and that geometry is an effective summary of deeper correlations. No boundary and tunneling say the beginning is a quantum state, not a classical event, and that the right question is how to define the wave function and extract predictions. Each answer is a lens, and each lens sharpens some features while blurring others. and each of these answers quietly asks the same forbidden question: why this framework, and why these laws, and why this state, rather than the countless alternatives that seem mathematically possible? We can trade a singularity for a boundary condition, but we cannot trade away explanation for free, because boundary conditions are themselves part of what needs explaining. The deeper we go, the more before becomes a demand for a new grammar, a way of speaking that does not assume time as a backdrop, not a timeline but a hierarchy of descriptions, where space-time is one effective chapter. In that hierarchy, the Big Bang is not necessarily the first event, but it may be the first place where our familiar variables, distance, duration, energy density, become well defined. The question, what happened before, may be like asking what a fluid was doing before molecules existed as a meaningful description. The universe may have had a prior description, yet not a prior time in the way we instinctively imagine. So we end this chapter with a practical pivot. If space-time and time can be emergent, then looking cannot mean seeing light in space, because light itself presumes a geometry to propagate through. It must mean inferring structure from surviving correlations in the data we can measure, and those correlations are statistical rather than pictorial. The realistic clues are spectra, phases, consistency relations, and relic backgrounds, patterns that can outlive the details of the transition that produced them. The honest goal is not to imagine a scene before the Big Bang. The goal is to identify which deeper frameworks can be squeezed by evidence and which remain unconstrained, and to be explicit about the difference. When models become too flexible, we should ask what would count as a failure, and whether the model risks becoming immune to the sky. When models make sharp predictions, we should ask whether those predictions survive the messy realities of measurement. The central question returns, now stripped to its hardest form. Did anything exist before the Big Bang, or is before the wrong category, a grammatical error imposed by brains evolved for mid-scale time and space? If time itself emerges, then the beginning is not a point behind us, because behind is a relation defined by time's arrow. It is a condition for the existence of behind and ahead, a rule that makes ordering possible. At the threshold where time and space may dissolve, before the Big Bang becomes less a place in history and more a test of what reality is made of, an invitation to replace certainty with better questions, and to let evidence, not intuition, decide what the beginning truly means. The mystery remains, but it is no longer a blank wall because we can name the constraints, the assumptions, and the possible observational hooks. In cosmology, progress often looks like learning which questions are well posed and which are artifacts of the language we started with. That is not surrender, it is refinement, and refinement is how science approaches the edge of its own concepts. Chapter 7 will try to close the loop without pretending the mystery is solved. We will ask what counts as an explanation when space-time is not fundamental, and how to distinguish a deep framework from a clever rephrasing. We will separate what is testable now from what might remain permanently out of reach, because honesty about limits is part of the discipline, and we will return to the simplest demand that never goes away. Whatever the beginning was, it left a universe we can measure. Before the first atom, before the first light, we asked what before could mean at all. That question is not poetic decoration. It is a technical problem about time, causality, and what counts as a physical clock. If time begins with the Big Bang, before may be like north of the North Pole, a direction that fails because the coordinate system ends. Yet some models restore an earlier phase, with clocks and change defined differently, and with beginning reinterpreted as a transition. Historically, this tension sits inside general relativity itself. Einstein's equations describe how space-time evolves, but they do not guarantee that space-time extends forever into the past. When Hawking and Penrose proved singularity theorems, they showed that under broad conditions, classical expansion implies an edge to classical history, an invitation to quantum gravity, not a final answer. So we translate looked like into physical state, not a literal picture. The camera cannot see anything in the ordinary sense because there are no stars, no atoms, and no transparent medium for classical light to travel freely. Even the word dark becomes a metaphor because darkness assumes eyes and photons and neither applies. In some proposals, even classical space is absent, so seen becomes a discipline metaphor, an inventory of fields, symmetries, and correlations. First candidate state is a contracting cosmos approaching a bounce. Space exists and shrinks, temperatures rise, and the cosmic horizon can behave in ways that mimic inflation's ability to set up large-scale uniformity. In a visual sense, the universe would look like a tightening geometry, with distances collapsing while quantum fluctuations are squeezed and amplified. Quantum gravity effects or exotic matter halt collapse, then reverse expansion without a singular point, turning an apparent ending into a dynamical turnaround. But contraction is dangerous, because small irregularities can grow fast. This bounce must control anisotropy, shear, and instabilities that typically amplify as the scale factor decreases. It must also deliver the observed near-scale invariant, nearly Gaussian, adiabatic perturbations that later become galaxies and voids. It must match BBN timing and the CMB's acoustic structure after reheating, because the light elements and the sky's harmonic peaks are unforgiving witnesses. Second candidate state is an inflating false vacuum background spawning bubble universes. A metastable vacuum dominates, expansion accelerates, and quantum fluctuations are stretched into classical density patterns that seed structure. Picture an immense, featureless expanse where space itself swells faster than signals can cross it, while tiny quantum jitters are promoted into macroscopic imprints. Local reheating inside a bubble becomes our hot Big Bang, while inflation continues elsewhere, generating more bubbles in an ongoing process. This picture multiplies beginnings and confronts the measure problem. Probabilities become ambiguous in an effectively infinite ensemble, and typicality becomes a choice rather than a theorem. The idea has roots in early inflationary thinking from the 1980s, when researchers realized that some inflationary potentials do not end everywhere at once. Other bubbles may exist forever beyond our horizon, separated by inflating space that expands too quickly for any message to cross, making direct confirmation unlikely. Third candidate state is a timeless quantum gravitational regime. Geometry is fuzzy, discrete, or emergent from deeper degrees of freedom and entanglement, so the familiar notion of earlier may not apply. The beginning becomes a boundary condition on a wave function, or a transition where time becomes meaningful as a coarse-grained thermodynamic parameter. Visually, imagine not a place but a rulebook, where what exists is a pattern of allowable relationships rather than a pre-drawn stage. Across these options, what is present is not emptiness but structure. Quantum fields still fluctuate, vacuum energy can dominate, and primordial correlations can be laid down long before atoms form. Some frameworks add higher dimensions, discrete spacetime elements, or holographic boundary descriptions, where information about a volume is encoded on a lower dimensional surface. Even when space is said to emerge, the mathematics still carries constraints that can echo forward into observables. Now we keep our forensic rule. Any prehistory must reproduce what survived into our sky, because cosmology is not free storytelling. The scoreboard starts with the CMB, large-scale structure, and light element abundances from BBN. These are not just data points, but interlocking consistency checks, linking expansion history, particle content, and the statistics of primordial perturbations. The CMB's temperature map is a fossil photograph of a plasma turning transparent, and its power spectrum is a coded record of sound waves in the early universe. Large-scale structure extends that record forward, showing how tiny initial contrasts grew under gravity into filaments and clusters. BBN reaches even earlier, because helium and deuterium abundances depend on the expansion rate and the number of relativistic species when the universe was minutes old. What we seek next are sharper fossils from earlier than recombination. Primordial B-mode polarization would test inflationary tensors and energy scales, because gravitational waves twist polarization into a distinctive curl pattern. A stochastic gravitational wave background could reveal bounces, phase transitions, or blue-tilted spectra, acting like a soundtrack from epochs otherwise hidden. These signals are difficult because astrophysical foregrounds and lensing mimic them, but the payoff is direct access to extreme physics. We also hunt relic particles and defects. Extra relativistic species would shift the CMB damping tail and the expansion rate, while axion-like fields could leave isocurvature traces or alter small-scale structure. Cosmic strings would carve line-like discontinuities and emit gravitational radiation, and primordial black holes would reshape early clustering and lensing statistics. Yet regions beyond our horizon, and most other bubbles, may remain permanently inaccessible, reminding us that evidence has a built-in boundary. Future pathways tighten the net. Next-generation CMB polarization missions push delensing and systematics, to reach smaller tensor signals, turning subtle patterns into quantitative limits. 21 centimeter cosmology maps vast volumes and new modes, probing initial conditions and exotic heating histories as neutral hydrogen glows and absorbs against the background. In principle, it offers a three-dimensional movie of structure formation, not just a two-dimensional snapshot. Gravitational wave observatories extend the timeline in frequency. Ground-based detectors, pulsar timing arrays, and space missions can bracket primordial backgrounds and constrain early expansion, because different frequencies correspond to different horizon entry times. Improved galaxy and lensing surveys test non-Gaussianity, isotropy, and subtle power spectrum features, looking for the fingerprints of specific mechanisms rather than generic early heat. So what can science claim today? We cannot confirm a single before, but we can map plausible histories and rule out many, using consistency across independent datasets. The singularity is likely not a literal beginning, but a boundary where classical general relativity stops being reliable, where quantum effects are no longer optional. That boundary may hide a bounce, an eternal inflating sea, or a regime where time is not yet a meaningful label. The universe may have a prehistory, or it may be self-contained with time emerging at the threshold. Either way, the mystery is productive, because it guides experiments and sharpens what counts as an explanation. When we ask what came before, we also ask what it would mean to measure it, and what kind of law can survive a change in the meaning of time. The deepest question may shift from what came before to why there is a universe with comprehensible laws. We return to the dark pre-light universe, defined by fields and hidden geometry. Then we return to the first detectable afterglow, the CMB's faint pattern of fluctuations, like a whisper preserved across 13.8 billion years of expansion. The earliest reality is not empty, but profoundly hidden, and still testable at the edge, where theory meets the last measurable trace. We began at the luminous wall of the cosmic microwave background, then worked backward by forensics, letting expansion, light element abundances, and faint anisotropies tell the story. Those clues lock in a hot, dense origin, yet they also expose a boundary, where general relativity drives toward a singularity and then stops making sense. At that Planck-scale edge, every candidate answer must pay the same price, match the CMB and nucleosynthesis, respect the arrow of time, and risk predictions that observations can actually break. From there, the possibilities split, not into fantasies, but into competing disciplines of restraint. Bounce models try to replace the singularity with a transition, but they must tame anisotropy, choose a vacuum without hand-tuning, and carry perturbations through the bounce without smuggling in the result. Inflation explains the universe's large-scale smoothness and the near-scale invariant seeds of structure, yet it may also be a veil, erasing earlier history and, in its eternal form, multiplying beginnings until probability itself becomes ambiguous. And the most radical ideas ask us to loosen our grip on the stage entirely, treating space-time and even time as emergent, built from quantum information, causal order, or a boundary condition that replaces a moment with a state. Along the way, nothing refused to stay simple, because physics does not recognize a blank page, only a physical configuration with rules, fluctuations, and constraints. The deeper we pushed, the more the universe looked less like an object in a container, and more like a set of relationships, fields, correlations, symmetries, waiting to become the geometry we call space. What survives every chapter is the method. Observations first, theoretical consistency second, and testability as the final gatekeeper, because the beginning is not a place for certainty, only for better questions. And still, one thread never loosened, because it is not optional for any origin story, the arrow of time. However the singularity is resolved, the early universe had to begin extraordinarily smooth, gravitationally low entropy, and oddly special, or else no galaxies, no chemistry, and no memories would ever form. Any before worth believing must explain not only how the universe expands, but why it begins in a state that allows a direction, a history, and a future. So the scoreboard remains open, but it is not empty. We know what any viable prehistory must reproduce, and we know what could still betray it. Primordial B modes, a stochastic gravitational wave background, relic particles, and extra radiation, cosmic strings, subtle non-Gaussianity, or features in the CMB and the 21 centimeter sky. If the universe had a prior phase, it may have left fingerprints, faint enough to miss, but stubborn enough to survive. In that sense, the documentary's journey does not end at a wall, it ends at a threshold. The Big Bang becomes less an explosion and more a boundary between descriptions, where familiar words like before, cause, and nothing begin to wobble. What we call the beginning may be a bounce, a branching, a tunneling, or a timeless state, but whatever it is, it must eventually answer to the sky we can measure. The central question was never only, did anything exist before the Big Bang, but whether before is a meaningful coordinate when time itself is part of the phenomenon. If time is born with the universe's geometry, then asking what came earlier is like asking what lies north of the North Pole, a grammatical impulse, not a physical one. But if time is emergent, or if a prior phase can be defined by different clocks and causal order, then before becomes a scientific claim, and the universe becomes a detective story with missing pages. So what did the universe really look like before the first light, when space and time were not yet fully formed? The honest answer is that it may not have looked like anything at all, because looking presumes light, distance, and a stable stage on which events can unfold. The better answer is that it may have been a state, quantum, relational, and constrained, whose only visible trace is the pattern we now read in ancient photons and in the distribution of galaxies. If that feels unsatisfying, it is also the most revealing result of all. At the edge of time, reality stops rewarding intuition and starts rewarding humility, because the universe is under no obligation to match the metaphors we grew up with. The beginning may be a moment, or a transition, or a condition, but it is not a story we get to finish by imagination alone. The final mystery, then, is not whether we can picture the pre-Big Bang universe in familiar colours and shapes. The mystery is whether the universe had to begin at all, or whether beginning is simply the name we give to the point where our current laws first become legible. In that gap, between what we can see and what we can meaningfully ask, cosmology becomes a quiet discipline, listening for the smallest surviving echo of whatever came before, and perhaps that is the most honest closure we can earn. We followed the evidence to the earliest light, we watched the equations warn us where they fail, and we mapped the few routes that might continue beyond that failure without turning into mythology. The universe may not grant us a picture of before, but it may grant us something rarer, a way to test our deepest assumptions about what time, space, and existence are made of. If you want to stand at that threshold with us, keep your eye on the next generation of measurements: delinced CMB polarization, multiband gravitational wave surveys, 21 centimeter cosmology, and every new constraint that forces the beginning to choose a single story. The Big Bang still isn't the universe's first moment. It is the first moment we can see, and the first moment our present physics can reliably translate. Push past that wall, and before becomes either a different kind of time or a sign that time itself is the thing that began. In the end, before the Big Bang is not a hidden room behind a door, it is a stress test for reality's foundations, asking what remains when space, time, and certainty dissolve. The beginning, whatever it was, is written less in our guesses and more in the faint, stubborn patterns the universe still carries. Stay curious, but stay disciplined, because the only way past the first light is to let evidence, not intuition, decide what beginning truly means.